When something from another star system drifts into our solar system, it raises more than curiosity. It sparks fear, wonder, and questions no telescope has fully answered. In 2025, scientists spotted 3I/Atlas, only the third confirmed interstellar object ever seen. Bigger, faster, and more chemically strange than its predecessors, Oumuamua and Borisov. It has stirred alarm. Could it do more than pass by? What is Atlas made of? Where did it come from? And could it pose more than just a fleeting cosmic spectacle? Scientists are both racing to study Atlas and quietly wondering what it might mean, not just in terms of astronomy, but in how we understand danger, origin, and what lies beyond our world. Cosmic wilderness: why interstellar objects are rare and hard to see. Out in the vast reaches of space, beyond the planets and their familiar orbits, lies a kind of wilderness. Here, the silence of the cosmic void stretches for light years, and every so often, through this emptiness, a lonely traveler passes by, a fragment of another star system. These are what we call interstellar objects, and they are among the rarest things we have ever managed to glimpse. The reason we have only spotted a handful so far comes down to just how difficult they are to see. An interstellar object was formed around another star, in another solar system, and somehow was ejected, maybe by a close encounter with a planet, or by the violent pull of gravity when its home system shifted. Freed from its star, it then spent ages moving alone through interstellar space until, by chance, it crossed into ours. The moment it does so, it becomes something unique, a piece of another world traveling through our neighborhood. But as amazing as that sounds, the odds of finding one are stacked against us. Space is vast, so vast that the distances between stars make even our solar system look tiny. While there may be countless rocks wandering between the stars, the actual density is incredibly low. Imagine standing in an open desert, miles from anyone else, and tossing a stone into the air. The chance of it hitting another person is almost zero. Interstellar objects drifting through the galaxy are like those stones. Billions may exist across the Milky Way, but compared to the emptiness they move through, they are scattered so thinly that the chance of one passing directly through our solar system is very small. That is why it took until 2017 before we even realized one had slipped past us. Oumuamua, the first confirmed interstellar object. Most interstellar objects are small, maybe 100 meters or so across, and they do not shine on their own. They only reflect sunlight, and if they are far from the sun, that reflection is weak, often too faint for telescopes to notice. When Oumuamua was discovered, it was already on its way out of the solar system. By the time astronomers realized what it was too late to study it up close. The same pattern happened with the second known interstellar object, 2I/Borisov. It was brighter because it acted like a comet, giving off a glowing tail of gas and dust, but even then, it was detected only when it was already inside our solar system. These examples show how little time we have to catch them. Part of the challenge comes from the way surveys of the sky have been done in the past. For most of history, telescopes were focused on specific targets: planets, stars, galaxies. Wide sweeps of the sky, done every night to search for faint moving dots, only began recently. Even then, these surveys had limits. Telescopes can only watch certain portions of the sky at a time. Some nights are lost to weather and others to the bright glare of the moon. The sensitivity of older instruments also meant they could not pick up the faintest objects until they were already quite close. With so much of the sky left uncovered, countless visitors could have slipped past unnoticed. It helps to think of the sky as a giant stage. Interstellar objects enter from the far edges, move across the stage for a very short time, and then exit again. If your spotlight only covers a small patch of the stage, you will miss almost all of them. That is what older surveys were like, narrow beams of light on an enormous dark set. The chance of catching one was like winning a lottery, which is why it is no surprise that it took so long to find even one. New survey telescopes are changing this picture. Instruments like the Pan-STARRS system in Hawaii, which first spotted Oumuamua, and the Vera C. Rubin Observatory in Chile, which has just begun operations, are designed to scan wide portions of the sky with incredible sensitivity. Instead of focusing on one spot, they sweep again and again, capturing moving objects no matter how faint. This approach greatly increases the odds of finding interstellar visitors before they vanish. Each pass of the survey acts like a wider spotlight, lighting up more of the stage and giving astronomers more chances to catch sight of something new. But even with these advances, the faintness of interstellar objects remains a problem. A rock 100 meters across, out near Jupiter's orbit, would be almost invisible against the black of space. Only when it comes closer to the Sun does it begin to brighten, reflecting more light. For comets, this process is stronger because the heat of the Sun makes them release gas and dust, which form bright tails. But if an object is rocky, like Oumuamua appeared to be, it may never get much brighter than a dim star. Astronomers need to catch it in that small window where it is bright enough to see but not yet gone too far. That window can be just a few weeks, which is why both known interstellar objects were observed so intensely in the short time available. This fleeting nature adds to the sense of wilderness. These objects are like wild animals crossing a trail in the night. There one moment, gone the next, leaving only faint tracks to study. We know they exist. We can estimate how many there might be, but most will slip through unseen. Our tools are improving, but the scale of space is against us. The rarity, the faintness, the limits of detection, all combine to make interstellar objects among the most elusive things in the sky. Most we will never meet, but once in a while, with the right telescope and a bit of luck, we catch sight of one, and for a moment, the wilderness of space feels a little less empty. Oumuamua, the first visitor that broke all the rules. In October 2017, astronomers in Hawaii noticed something unusual while scanning the night sky. Using pan-stars, a system built to detect near-Earth asteroids, they spotted a faint dot of light moving faster than expected. At first, it looked like any other small body drifting through space. But within days, as the data was checked and compared, it became clear this object was something different. Its path through the solar system was not the kind of orbit we see with comets or asteroids tied to the Sun. Instead, it was flying on a trajectory that showed it had come from far beyond, moving too quickly ever to be captured by the Sun's gravity. This was the moment when humanity realized it had just seen its first confirmed visitor from another star system. The object was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. At first, scientists tried to fit Oumuamua into the categories they already knew. Was it a comet? Was it an asteroid? Those were the two main types of small bodies that move through our solar system, and all past discoveries could be sorted into one or the other. But almost immediately, Oumuamua refused to cooperate. For one thing, it showed no coma, the glowing halo of gas and dust that forms when comets heat up near the Sun. There was no tail streaming behind it, no sign of icy material boiling away. That suggested it was rocky, more like an asteroid. But even that didn't quite fit, because its speed and path still seemed odd. Then came its shape. As more measurements were made, astronomers realized that Oumuamua's brightness changed dramatically as it rotated. That meant it wasn't round or even gently lumpy like many asteroids. Instead, it seemed extremely stretched out, like a cigar or maybe a pancake, depending on how the data was interpreted. No object in our solar system looked quite like it. Most asteroids are roughly spherical or potato-shaped, but this one had an aspect ratio far beyond what had been seen before. The idea of a cosmic shard, an elongated fragment, began to take shape, and it added to the sense that this visitor was something strange. The puzzle deepened when astronomers tracked Oumuamua's motion more closely. After passing near the Sun, its path didn't quite follow the curve expected from gravity alone. It was accelerating ever so slightly, as if pushed by something extra. Normally, a comet shows this kind of behavior because jets of gas shoot out from its surface, acting like thrusters. But Oumuamua had no visible gas jets, no tail, nothing that looked like comet activity. Yet it was moving as though some gentle push was nudging it along. Scientists offered different explanations. Some argued that perhaps Oumuamua did have outgassing, but it was invisible or too weak to produce a normal tail. Others suggested it might have been made of unusual material, like hydrogen ice, which could evaporate in a way that leaves no obvious trace. Another idea was that it might be a shard of nitrogen ice chipped off from the surface of a Pluto-like planet around another star. Each explanation tried to account for its strange behavior without calling it something entirely new, but none of them could be proven with certainty. The uncertainty fueled debate. Some researchers went further, speculating about even more unusual possibilities. One suggestion that captured the public imagination was that Oumuamua might be artificial, a kind of probe or fragment of technology from another civilization. This was not the mainstream view among astronomers, but the fact that the object was so strange made the idea linger in the background. After all, if nature had never produced something quite like it in our solar system, could it be a sign of something made rather than born? Most scientists leaned away from that conclusion, but the fact it was raised showed how wide the questions had become. It was faint, moving fast and only visible for a few short weeks, before it faded from view. By the time the world realized how extraordinary it was already too late to send a spacecraft or capture clearer data. Everything we know comes from the brief window when telescopes tracked its path across the sky. As a result, its true nature remains unsettled. Was it a fragment of rock shaped by violent forces? Was it a chunk of exotic ice? Was it something we have never seen before, perhaps unique to the conditions of another star system? Even now, years later, no single explanation satisfies everyone. Its lack of a visible tail, its elongated form, and its unexplained acceleration each break a rule of what we thought comets or asteroids should be. It did not neatly fit the boxes we had built, and it forced astronomers to realize that the solar system might only show us a small fraction of what exists. The galaxy could be filled with objects shaped and formed in ways our local examples cannot prepare us for. In the time since its discovery, computer models have tried to imagine how objects like Oumuamua could form. Some simulations suggest collisions in other systems might throw out fragments shaped like long needles. Others show that ice-rich bodies exposed to heat could evaporate in odd ways, leaving behind thin or flat remains. Still, these are guesses, attempts to fill in the gaps with theory when direct evidence is gone. Oumuamua itself is now too far away, traveling into the dark between the stars, never to be seen again. 2. Borisov, a more typical comet from outside. In late August of 2019, just 2 years after Oumuamua had stunned astronomers, another discovery shook the scientific community. This time, it came not from a large observatory or a wide-field survey, but from the careful work of an amateur astronomer in Crimea. Gennady Borisov, using a telescope he had built himself, spotted a fuzzy object moving against the backdrop of stars. At first, it looked like one of the many comets that pass through our skies each year. But soon, its orbit was calculated, and just like Oumuamua before it, the object's path showed it was not bound to the Sun. It was the second known interstellar object, and the first that clearly looked and behaved like a comet. It was officially named 2I/Borisov, with the 2I marking it as the second interstellar visitor recorded by humanity. Unlike the mystery of Oumuamua, Borisov seemed familiar from the beginning. It had a visible coma and a long glowing tail streaming away from the Sun. Telescopes easily picked it up because it was producing the same kind of activity that solar system comets do when their icy surfaces heat up. As soon as the news spread, observatories across the world pointed their instruments toward it. This was the first time astronomers could watch an interstellar comet unfold in detail, and they were eager to learn whether it truly was like the comets born in our own system, or whether it carried new surprises. Borisov's composition, revealed by the light it reflected and the gases it released, closely matched that of ordinary comets. It gave off water vapor, carbon monoxide, and other simple molecules. Its dust grains resembled those seen in comets from our own Oort cloud, Even its appearance, bright nucleus, glowing coma, long tail, fit the textbook image of what a comet should look like. To many scientists, this was a reassuring discovery. If interstellar space is filled with comets like Borisov, then our solar system is not unique. The same processes that formed comets here are happening around other stars as well. Still, Borisov was not just a duplicate of our local comets. Careful measurements showed that in some ways, it was more pristine. Many comets in the solar system have made several passes near the Sun, and each time they lose some of their ices and develop surfaces that are less fresh. Borisov, by contrast, seemed untouched, as though it had never before approached any star closely. Its ices were rich, its gas emissions steady, and its overall activity more vigorous than expected. This suggested that it had been traveling through space for a long time, perhaps since the early days of its home star system, and was only now experiencing significant heating for the first time. This showed that the processes of planetary formation, where icy bodies are flung outward into distant orbits and sometimes ejected into interstellar space, are not unique to our Sun. Somewhere out there, around another star, Borisov must have been part of a family of icy bodies, shaped by gravity and collisions, until one day it was kicked out into the galactic wilderness. Its journey might have taken millions or even billions of years before it happened to cross paths with our own solar system. With the first interstellar object, scientists were left unsure whether it represented something typical or something rare. Was Oumuamua strange because it was unusual, or was it strange because our sample size was too small to know better? Borisov provided a counterpoint. Its normalcy showed that interstellar visitors can, in fact, resemble the comets we already know. This helped calibrate expectations. Future interstellar objects might look more like Borisov than like Oumuamua, making them easier to recognize. Still, even in its normalcy, Borisov carried mysteries. The exact ratios of its gases were slightly different from many local comets, hinting that while the general recipe for comets may be universal, each star system may add its own variations. Some studies suggested that Borisov contained higher levels of carbon monoxide than most solar system comets. If true, this could mean it formed farther out in its home system, where it was colder or perhaps in an environment richer in certain ices. Details like this act like fingerprints of a comet's birthplace. By studying Borisov, scientists could begin to piece together the chemistry of a world we will never see directly. As Borisov approached and then passed the Sun, astronomers watched closely to see how it behaved. Its steady production of gas and dust confirmed that it was active all the way through. But by early 2020, signs began to appear that the comet was breaking apart. Images suggested its nucleus was fragmenting, perhaps under the stress of solar heating. This too was a familiar story. Many solar system comets, when making close passes near the Sun, have split into pieces or faded into dust. Borisov, in its final act, showed once again that the processes shaping comets are shared across the galaxy. Borisov was bright enough and active enough to attract the full attention of Earth's observatories, and for months it became the subject of intense study. Each measurement added another piece to the picture, helping to turn what could have been just a fleeting blur into a record of another world's history. The gap between Oumuamua and Borisov lessens in expectation. After Oumuamua, one of the biggest shifts in thinking was about comet activity. For decades, astronomers had predicted that if an interstellar object ever entered the solar system, it would most likely look like a comet. This expectation came from the fact that comets are formed far from their stars, in cold outer regions where icy material can build up. In such environments, the chance of being ejected into interstellar space is higher, because icy bodies often interact with giant planets that can fling them out. The theory was that the majority of interstellar visitors would carry frozen ices within them, and when warmed by our Sun, would produce the characteristic halo and tail of a comet. Oumuamua seemed to disprove that expectation. It showed no coma, no tail, and no clear sign of gas emissions. At first glance, It looked like a rock rather than a comet, which suggested that maybe interstellar space was filled with fragments of broken planets or asteroids instead. Some scientists proposed that collisions in distant star systems might produce more rocky debris than icy comets, changing the balance of what kinds of objects drift into interstellar space. Others suggested that Oumuamua had once been icy, but had lost its volatiles during a long journey, leaving only a bare core behind. Whatever the case, the prediction that interstellar visitors would look like comets suddenly seemed less certain. Then Borisov appeared, and with it came confirmation that the original expectation had not been entirely wrong. Borisov behaved just like a comet from the start. The differences between Oumuamua and Borisov were stark, and this forced astronomers to revise their models again. Rather than assuming all interstellar objects would behave one way or another, the picture became more flexible. Some visitors might resemble icy comets, fresh and active, while others might resemble rocky fragments that had lost their volatile material. Interstellar space, it turned out, might deliver both types. Oumuamua and Borisov represented two ends of a spectrum. One was dry and mysterious, the other wet and familiar. If both could exist, then the galaxy must be filled with a wide range of interstellar debris, each shaped by its own history. Astronomers began to update their models to account for this diversity. Some objects might be ejected early in their system's life, preserving their icy shells, while others might spend millions of years close to their star before being thrown out, losing much of their frozen content along the way. Another expectation that was challenged concerned the stability of orbits. Before Oumuamua, most simulations assumed that interstellar objects would pass through quickly but predictably, following neat hyperbolic paths shaped only by the sun's pull. Oumuamua's slight acceleration suggested otherwise. Something beyond gravity was at work, whether it was faint outgassing or another unknown force. That opened the possibility that interstellar objects could be more dynamic than predicted, with small but important changes in their speed and direction as they warmed near the sun. When Borisov was studied, its orbit largely fit the predictions. It moved on a hyperbolic path that matched expectations for an interstellar comet. Its acceleration was consistent with the outgassing seen in normal comets, with no need to invoke mysterious forces. In this way, Borisov acted as a calibration point. It showed that, in many cases, interstellar objects will behave as theory suggested, with predictable orbits and explainable comet activity. Oumuamua, then, might represent a rare or unusual case, while Borisov reflected the more common behavior. The appearance of interstellar objects as they approach the Sun also became a subject of renewed study. Before any were discovered, the assumption was simple. Objects would brighten steadily as sunlight heated them, and comets would develop tails while rocky bodies would remain faint. Oumuamua complicated this picture because it brightened and dimmed in strange ways, likely due to its unusual elongated shape. Its changes in brightness were sharper than what was seen with ordinary asteroids, making it more difficult to interpret. Borisov, as it came closer to the Sun, brightened in a smooth, predictable way. Its coma grew larger, its tail stretched farther, and its brightness curve matched those of comets within our solar system. This provided scientists with a sense of normalcy. They could compare their models of how icy bodies heat up and release gas with real data from an interstellar comet, and the fit was reassuring. Borisov restored confidence that the theories built from local comets could apply more broadly to the galaxy. The first object forced scientists to consider possibilities they had not before. The second object grounded those ideas, confirming that some predictions were still sound. Together, they created a framework for future discoveries. The mix between the two remains uncertain, but both categories are now firmly on the table. This shift in expectations also influenced how new surveys are planned. Since interstellar objects might be faint and strange like Oumuamua, telescopes must be sensitive enough to catch fast-moving points of light with unusual brightness patterns. At the same time, since they might also be bright and comet-like like Borisov, Wide coverage of the sky is necessary to catch their tails and comas as they flare up. By considering both extremes, astronomers are better prepared to catch whatever nature delivers next. The processes that form planets and comets are chaotic, influenced by collisions, migrations of giant planets, and the shifting birth environments of stars. What gets thrown into interstellar space will reflect that chaos. Each will carry a story, and no two will be exactly alike. By comparing the two, scientists also gained insight into the possible lifespans of interstellar objects. Oumuamua may have been altered by long exposure to cosmic radiation, its surface darkened and its ices depleted during a long journey. Borisov, meanwhile, seemed fresher, suggesting it may not have been traveling for quite as long. These differences hint that interstellar visitors could come in many stages of age and preservation, from ancient weathered fragments to relatively young icy wanderers. The challenge will be to sort out these histories from the limited data available during their brief visits. Discovery of 3 I/Atlas, when the sky survey workers raised alarms. The discovery of 3 I/Atlas in 2025 marked a new moment in humanity's watch of the skies, one where scientists saw a probable interstellar visitor early and many observatories quickly joined in the chase. The chain of detection, the role of archival data, and the speed with which the community recognized its interstellar nature tell us a lot about how our ability to spot cosmic visitors has grown. On the 1st of July 2025, the ATLAS, or the Asteroid Terrestrial Impact Last Alert System survey telescope in Rio Hurtado, Chile, first reported what would become known as 3 I/Atlas. At that time, Atlas flagged a moving point of light that seemed to be entering the inner solar system from far away, moving roughly at magnitude 18. Immediately after that, astronomers began digging into pre-discovery or pre-covery observations, images that had been taken before July 1st but had not been identified as this object yet. These pre-covery images came from several sources: other ATLAS telescopes around the world, the Zwicky Transient Facility, or ZTF, at Palomar Observatory, and even TESS, the Transiting Exoplanet Survey Satellite. For example, the ZTF had observations from the last few days of June that were found within hours of the initial report. Earlier still, there were ATLAS images from the 25th to the 29th of June. TESS provided data from the 7th of May to the 2nd of June 2025, roughly 2 months before the formal discovery, showing that the object was present, though very faint. Stacking of those TESS images revealed a light curve and confirmed that activity may already have been underway. Using all those images, discovery plus precovery, astronomers refined the object's orbit. They found that 3 I/Atlas is following a hyperbolic trajectory. Its orbital eccentricity was measured to be very high, about 6.2, which is far above what is needed just to be unbound. The hyperbolic excess velocity, or velocity the object has as it enters the sun's influence, above what's needed to escape, was large, on the order of about 60 kilometers per second. These properties told scientists quickly that this was not a long-period comet returning from the outer reaches of our solar system, but a visitor from beyond. At the time of discovery, 3 I/Atlas was about 4.5 astronomical units from the Sun. That distance is large enough that many comets are nearly inactive or very faint, but still within the range of the better survey telescopes. Atlas picked up the object while it was still far out, which meant astronomers had more lead time than in previous interstellar object discoveries. Once Atlas reported the discovery, dozens of observatories worldwide started observations, optical telescopes to watch its movement, spectroscopy instruments to analyze its gas and dust, and space telescopes like Hubble and Webb to see details that ground-based telescopes might miss. Because precovery data were already gathering in from multiple sources, the orbit could be refined quickly, allowing better predictions of its path, brightness changes, and when it would get closest to the Sun. Where in the sky it came from is also telling. The direction from which 3 I/Atlas is inbound, is roughly from the constellation Sagittarius, near the dense region toward the center of our galaxy. That is somewhat unusual compared to what many had predicted for interstellar objects, which were expected more often from nearer star directions or from the solar motion direction. The fact that it came from a crowded region of the sky also made early detection harder. Dense star fields make it difficult to pick out a moving object because there are so many background stars and so much noise. This may explain why, even though precovery images existed, the object was not flagged earlier. When enough of the orbit could be calculated, the eccentricity well exceeded 1 in a clear way. The breadth of the observational arc, thanks to pre-discovery images, and the involvement of many observing stations allowed for correction of early uncertainties. Because the object had been seen earlier, astronomers could measure its change in position over a long period, reducing the errors in orbit calculations. Within a day or so of the discovery report, observations from several telescopes found evidence of a faint coma and a tail-like elongation of about 3 arc-seconds. This early identification of activity helped classify 3I/Atlas as a comet rather than a bare rock, which also made comparisons with other interstellar comets more meaningful. In terms of speed, this discovery and follow-up were much faster than for either Oumuamua or Borisov. With Oumuamua, scientists realized its interstellar nature only after it had passed near Earth, and many features were ambiguous by then. With Borisov, detection of cometary features was present, but still required time and coordination. 3I/Atlas was flagged, pre-covery data pulled, and activity confirmed, all in a matter of days to weeks. That rapid response means better data, earlier study, and more chance to observe how the object changes as it approaches the Sun. Because of this early observation window, scientists are getting a better look at how 3I/Atlas behaves over time, how its coma grows, how gases are released, how brightness changes with distance from the Sun. In particular, the James Webb Space Telescope observed it in early August, when it was still several astronomical units from the Sun, and found its coma is rich in carbon dioxide, with water and other gases present, but water weaker in proportion than in many solar system comets. That suggests that 3I/Atlas may have formed in a cooler or different environment than many comets in our own system, or that its ices have been preserved well. Because astronomers caught 3I/Atlas while it was still relatively far from the Sun, it helps fill in gaps between what we saw in Oumuamua and Borisov. Scientists can watch how its coma forms, how its activity ramps up, and how its materials respond to sunlight over time, not just as a brief flash when it is already near perihelion, but over months. Orbit and motion. Why Atlas's path raised eyebrows. The path that 3I/Atlas follows through the solar system is one of its most striking features, and it's what made scientists raise their eyebrows right after its discovery. Its orbit and motion hold clues both about its origin and about how unusual it is compared to typical solar system comets. When astronomers say orbit, one thing they often look at is eccentricity. That tells how open an orbit is. 0 means a perfect circle. Between 0 and 1 means an ellipse, closed like planets. Exactly 1 means parabolic, or barely unbound, and greater than 1 means hyperbolic, or clearly unbound. For 3I/Atlas, the eccentricity is not just above 1, it's very high. According to the measurements, its eccentricity is a bit above 6. This means its path is very open. It plunges in, passes by, and heads back out of the solar system much too quickly to be bound by the Sun's gravity. Another important number is the incoming velocity at infinity, which is how fast the object is moving before the Sun's gravity starts accelerating it as it approaches. For 3I/Atlas, this is measured around 58 kilometers per s relative to the Sun. That is fast. Faster than what most long-period comets moving in from the outer solar system typically have. Astronomers measure orbital inclination, which is how much the orbit is tilted relative to the general plane in which planets orbit, called the ecliptic. For 3I/Atlas, the orbit is retrograde and inclined only a few degrees off the ecliptic, about 175 degrees. A retrograde orbit means it moves in the opposite direction of the planet's motion. So although its path is not wildly tilted, the fact that it's retrograde is significant. At its closest approach to the Sun, 3I/Atlas will come within about 1.36 AU of the Sun. That's inside the orbit of Mars, which orbits at about 1.5 AU, but outside Earth's orbit. Because of its orbit and speed, when it gets near the Sun, it's moving much faster still, thanks to gravitational acceleration. These orbital parameters, high eccentricity, high incoming velocity, retrograde motion, are very different from typical solar system comets or asteroids. Many comets in our solar system have more gentle, bound orbits, with eccentricity well less than what 3I/Atlas has, lower incoming speed and prograde motion. That is the same general direction as planets. The unusual path of 3I/Atlas made it clear early on that this was no ordinary solar system body. Because its orbit is hyperbolic, it will not come back. It will swing through once and leave, never to return. That means the window for observing it is limited. Also, the fact that its perihelion is relatively far, and that it won't get closer than about 1.8 AU to Earth, means that although its path is dramatic, it will not come dangerously close to Earth. Still, when it was first discovered, the speed and trajectory caused some concern and speculation. Any object entering on a hyperbolic high-speed path raises the question, could it cross Earth's orbit or even pose an impact risk? In the case of 3I/Atlas, early orbit calculations, with limited data, sometimes had large uncertainties, leaving room for possible nearer approaches. But as more observations and precovery images came in, those uncertainties narrowed. It became clear that its closest approach to Earth would be around 1.8 AU. Because it's coming from interstellar space at high speed, encountering objects like that inside the solar system produces interest not just because of what they are, but because of what forces they must endure. Radiation, heating, tidal forces, possibly collisions, but also how fast they brighten or how their surfaces respond. For 3I/Atlas, scientists saw early that its incoming speed is higher even compared to Oumuamua, which had excess velocity approximately 26 km/s, and Borisov, about 34 km/s. So 3I/Atlas is pushing the upper bounds of what was expected. The retrograde inclination also matters, because retrograde comets cross the paths of planets in opposite directions, which causes relatively higher relative velocities when crossing orbits. That can increase the chance, in principle, of interactions or collisions. Because of that, early warnings and orbit refining are necessary to be sure whether a new object might have any Earth-crossing potential. Orbit orientation influences when and where in the sky the object is visible, when it is heated, how its tail is illuminated, and how easy or hard the object can be studied. For 3I/Atlas, the argument of perihelion puts its closest approach to the Sun on the opposite side of the Sun from Earth, which means Earth-based telescopes will miss some of the most active part of its perihelion passage. Because the object will be close to the Sun, from our viewpoint, when near perihelion, and because it is behind the Sun as viewed from Earth, observations during that peak heating will be challenging. This can limit how well scientists can see changes during its hottest and most active time. Sizing up Atlas. When 3I/Atlas was first spotted, the early size estimates were very rough. Observers saw a fuzzy bright object and knew there was a coma. But separating what light comes from the solid icy or rocky nucleus versus what comes from the coma is tricky. So early diameter estimates, or radius estimates, often assumed a lot, or even most of the light was from the nucleus, which tends to make size numbers large. Some early ground-based estimates said the nucleus might be as large as 10 kilometers across. Others even floated numbers up around 20 kilometers based on brightness measurements under certain assumptions of reflectivity and how much light coma contributes. But later, better observations refined those numbers downward. High-resolution imaging from the Hubble Space Telescope placed an upper limit on the nucleus diameter of about 5.6 kilometers. At the same time, Hubble ruled out much larger sizes by not seeing a solid body that large distinct from the surrounding coma. It also set a lower limit in some cases. Hubble observations show the nucleus radius must be less than about 2.8 kilometers, assuming a typical albedo of around 0.04. Some observers also suggest the nucleus could be much smaller, possibly as small as 320 meters in diameter, though that lower bound assumes more of the light is from dust and gas in the coma, and very little from the nucleus itself. So across various estimates, the diameter might be somewhere between 0.3 kilometers and 5.6 kilometers, though many think the true size is toward the lower end of that range due to the dominant coma. Brightness measurements are expressed in various ways. One important measure is absolute magnitude, often denoted by H, which is how bright the object would appear at a standard distance from both the Sun and the observer, removing the effects of distance. For comets, brightness includes both nucleus and coma. Because comets have comas, the light is often boosted by the surrounding dust and gas. For 3I/Atlas, different teams using different telescopes, ground-based, space-based, have derived H values somewhere around 12 to 13 in the V or visual band. But the H value for the nucleus alone may be much dimmer, because much of the observed brightness comes from the coma. These brightness numbers have shifted over time as better telescopes, better images, and more data came in. As of early observations, people working with ground-based telescopes saw brightness consistent with a large reflecting area, so size estimates were large. Later, when Hubble images with better angular resolution were used, scientists saw that a lot of that reflected light blurred with the coma, meaning the nucleus itself must be smaller to match the observed light if the albedo is typical. JWST and other infrared/near-infrared data help by seeing what kind of gases are producing the coma, which in turn helps estimate how much dust is there, which affects how bright the comet looks, but not how big the solid core is. A comet's coma is bright because dust and gas reflect sunlight or emit light via gas emissions over a large area. If the coma is thick or large, it may contribute most of the light seen, even though the solid nucleus is much smaller. If one does not subtract coma light carefully, one might think the nucleus is far larger than it actually is. For 3I/Atlas, this was exactly the issue. Early estimates assumed more of the light came from the nucleus. How much sunlight the surface or dust reflects changes greatly what size corresponds to a certain brightness. A dark surface reflects little light, so needs to be larger to produce a given brightness. A lighter, more reflective surface or very bright dust can make a smaller object appear quite bright. If you assume a too bright albedo, your size estimate shrinks. If you assume a too dark albedo, size estimates grow. Astronomers often assume 0.04 to 0.05 for comet nuclei, but that is an assumption and can be wrong depending on composition. How far the comet is from the Sun and Earth and the angle of illumination all affect how brightly we see it. As the comet draws nearer to the Sun, it warms, the coma gets stronger, more dust is shed, so brightness can increase sharply. But that doesn't necessarily mean the nucleus is big. It means activity is strong. Also, if Earth is seeing it more fully lit, brightness increases. Observations over time reveal trends of brightness rising, but those trends are not simple indicators of size. Some gases can drive out dust far more when warmed, some less. If gases like carbon dioxide or carbon monoxide are abundant and active early, then the coma may develop sooner at larger distances. That adds to brightness early, before the nucleus receives much heat. In the case of 3I/Atlas, JWST measured a high CO2 to H2O ratio, meaning CO2 activity is strong and may contribute to the coma, and thus to brightness earlier than water sublimation would. As more data accumulates, particularly from high-resolution imaging like Hubble, spectroscopy, and careful coma nucleus modeling, astronomers will narrow down the true size. Each better telescope or method tends to pull the size down or at least sets tighter upper limits. Atlas's outgassing and tail morphology. 3I/Atlas's coma appears not just round, but elongated in some images, especially early ones. For example, there is a sun-facing plume or extension in the coma, pointing toward the sun and toward the object's motion. This means that as the sun warms the comet, dust and gas are being emitted from the side facing the sun more strongly, creating a brighter, extended part of the coma in that direction. As the comet has moved closer to the sun, its tail has become clearer. Observations from instruments like Gemini South in late August 2025 showed that 3I/Atlas had developed an anti-solar tail, that is, a tail pointing away from the sun. Earlier, the tail was faint or short, and sometimes hard to distinguish from the coma. But by late August, that tail had become more visible and somewhat extended. The tail being anti-solar is typical for comets. Dust particles released from the comet get pushed by solar radiation pressure outward, forming a tail that points away from the sun. For 3I/Atlas, the tail's appearance has grown with time and its length has increased as well. Observations suggest that by the end of August its anti-solar tail was more obvious, with the inner coma still showing sunward features. In particular, there is a measured change in tail and coma behavior. The coma's shape, brightness and color have been changing with time and with distance from the sun. Based on photometry by the Atlas network, there's a slope break in how brightness evolves as the object comes in. Before about 3.3 AU from the sun, the comet was brightening at one rate. Closer than that, the rate changed, slowed or modified, as more small, bright, icy grains and changes in coma optical depth dominate. The gas-dust composition of the coma is unusual in some ways, especially compared with many solar system comets. Notably, JWST measured a coma dominated by carbon dioxide, with water, carbon monoxide, OCS, dust, and water ice also present. The ratio of CO2 to H2O is very high, around 8:1, one of the highest observed in a comet. This suggests that CO2 is playing a primary role early, perhaps because CO2 is volatile enough to sublimate at larger distances from the sun than water ice. Because CO2 outgassing occurs further from the sun, 3I/Atlas shows visible coma activity earlier than some solar system comets that are dominated by water evaporation. That means its coma is growing while still relatively far out, around 3 to 4 AU, rather than waiting until nearer to the sun. There is also variability in the coma and tail. The brightness of the coma is changing. Observations showed that the comet transitioned in color from red, when it was farther out, toward colors closer to neutral as it neared the sun, and as the tail became more obvious. That suggests the types of particles being emitted are changing, maybe smaller, brighter icy grains becoming more prominent, or dust behavior changing. The sun-facing plume or coma elongation is also variable. In July and early August, the comet's coma was noticeably elongated toward the sun, indicating stronger emission on that face. Then, as time passed and geometry changed, both of the comet's position relative to Earth and the sun and its heating, the anti-solar tail became more visible, sometimes dominating. Many solar system comets begin strong activity closer to the sun. At large distances, of about 3 to 5 AU, water ice is less active. Some comets with high carbon monoxide or CO2 content show activity further out. Borisov showed comet-like activity, coma, tail, gas emissions, once it was closer, but did not show CO2 dominance as strongly early on, at least not to the level seen now in Atlas. So Atlas's early CO2-driven coma is among its more unusual traits, putting it somewhat between typical comets and an extreme. Borisov had classic tails and gas jets that could be followed over many weeks. Atlas's tail is emerging and it is faint at first, then growing. The morphology, aka how extended, how broad, how sharply defined it is, has changed over time. It was initially more compact, fuzzy, and then got more extended and more recognizably tail-like. Also, the inner coma is showing shape changes, with fan-shaped features, brighter sunlit side, etc. These are similar to what active comets do, but the magnitudes differ. Atlas stands out in its very high CO2 to H2O ratio, more than most solar system comets, and also more than Borisov in some observations. That means the materials exposed on its surface or near surface are richer in more volatile ices, or the comet has layers or structure that suppress water sublimation. It could also mean its formation region was colder or had a different chemistry. In addition to the anti-solar tail, which is growing, some of the images show that the tail's angular size has increased. In late August, observations via Gemini South showed the tail at tens of arcseconds long, whereas in earlier images it was much shorter or barely resolvable beyond the coma. Further observations show a teardrop-shaped cocoon of dust emanating off the nucleus. The coma is not symmetric, but shows structure, an extended region of dust trailing or surrounding the nucleus, brighter in certain directions. When the tail is pointed toward Earth or foreshortened, it may appear less extended or less distinct. Bright background stars, distance and instrument sensitivity limit what faint tail features can be seen. Dust grains of different sizes also respond differently to solar radiation pressure. Atlas seems to be ejecting a mix: small, bright icy grains, dust plus gas emissions, and possibly larger particles in the inner coma. Overall, Atlas's coma and tail behavior is already richer and more active than what was seen for Oumuamua, and is somewhat more extreme in certain gas composition traits than Borisov at comparable distances. It resembles many solar system comets in general behavior, but the timing, composition, and detailed morphology make it stand out. What Atlas is made of. Using JWST. On August 6, 2025, astronomers took infrared spectra of 3I/Atlas with its NIRSpec instrument. The spectrum covered wavelengths from about 0.6 to 5.3 microns. Along with the CO2, water vapor, and carbon monoxide already mentioned, JWST also detected carbonyl sulfide, or OCS, water ice grains, and dust in the coma. Production rates, how many molecules per second the nucleus is releasing, were estimated. There are also terminal or whole coma estimates that show somewhat higher values for CO2 and bigger mixing ratios relative to water once effects like optical depth and gas-dust interactions are accounted for. Water ice grains were observed. Tiny particles of water ice in the coma were seen via absorption features. That means that some ice is being ejected, not only gas, and that ice persists in small grains in the coma. Compared to typical comets in our solar system, 3I/Atlas stands out in several ways. Most comets closer to the Sun tend to have water vapor as the dominant gas produced when warmed. In those solar system comets, water begins to sublimate more strongly as the comet warms, so water tends to dominate. Carbon monoxide is present at levels more in line with comets we know. Not surprisingly high, but significant. The carbon monoxide to H2O ratio in Atlas lines up with values seen in some long-period comets, or even what was seen in 2I/Borisov under certain conditions. OCS is weaker, but detected. OCS is one of the sulfur-bearing gases. Its presence adds richness to the chemical mix, showing that not just the simple ices, but more complex volatile species are part of what Atlas is carrying. The presence of water ice grains, small icy particles in the coma, means ice is being lifted out. Not all of the ice is buried or locked up. Some is being ejected. This is similar to what is seen in other comets, but again the balance between gas, ice, and dust is unusual in Atlas because of the dominance of CO2. The unusually high CO2 to H2O ratio hints that the nucleus is intrinsically rich in CO2 ice. That means when it formed in its home system, conditions allowed CO2 ice to be abundant and preserved. Possibly Atlas formed beyond the CO2 ice line of its star's disk. That is, at a distance where temperatures were low enough for CO2 to freeze out, and where water ice formation or exposure may have been less dominant. Alternatively, or in addition, water's release could be suppressed because of an insulating crust, or because heat does not penetrate deeply into the nucleus. If water ice lies beneath a surface layer that is not very heat permeable, then even when some warming happens, water vapor may not escape strongly until later. Meanwhile, more volatile ices like CO2 and carbon monoxide, which sublimate at lower temperatures, are able to drive outgassing earlier or more easily. Another suggestion is that Atlas may have been exposed to higher levels of radiation or other space weathering in its journey or in its parent system. That may have altered surface layers, perhaps depleting water or burying it, or causing changes that make CO2 dominate in the activity. Radiation tends to erode or destabilize more volatile ices, or can produce crusts from dust and organics that limit gas flows. Because these spectral measurements are fairly new, there are still open questions. How uniform is the composition over the nucleus surface? Does one side have more exposed volatile ices, or are some regions masked by dust or crust? The sunward direction shows enhanced outgassing in the JWST data, so there's asymmetry. How does the composition change as 3I/Atlas moves closer to the Sun? Will water begin to take over more of the outgassing, or will CO2 continue to dominate? Monitoring over time helps determine if the behavior shifts as solar heating increases. How deep is the volatile ice located beneath the surface, and how much thermal insulation exists? This affects how quickly water ice warms and contributes to the coma. What about the ratios of isotopes, for example carbon-12 versus carbon-13 in CO2, and other trace species? Those can act like fingerprints of the environment where Atlas formed. JWST measured some limits on the different carbon isotope ratio, finding a lower limit that is consistent broadly with solar system values, but with uncertainties. Putting it all together, these findings help refine what astronomers expect future interstellar comets might be made of. Because Atlas is so well studied, it becomes a reference point. An interstellar comet rich in CO2 with weaker water emissions at distance, with dust and ice grains, and a mixing of gases that hints at both similarity and difference to solar system comets. Was Atlas already active in the outer solar system? While 3I/Atlas was still far from the Sun, satellite observations picked up faint signals in pre-discovery data. TESS observed the region between May and June, before Atlas officially discovered the object in July. In these TESS images, 3I/Atlas was too faint to stand out on each individual exposure, but by stacking many images, astronomers could pull out a light curve. From those stacked TESS observations, researchers found that 3I/Atlas had an average magnitude of around 20. They also found that its brightness at that distance was similar to what it showed after discovery, suggesting that it may already have been active, producing dust or gas that boosted its brightness beyond what a bare nucleus would do. Parallel to the TESS findings, ZTF and archival survey images from Atlas found that 3I/Atlas followed a fairly steep brightening rate in its inbound leg. A brightening rate means how quickly its brightness increased as it approached the Sun. For 3I/Atlas, the brightening was steeper than what was seen for 2I/Borisov, more like what is observed in dynamically old long-period comets in our solar system. Specifically, the data suggests that 3I/Atlas had been ejecting dust by early May 2025 at a rate of about 5 kilograms per s. By mid-July, when it was closer, that dust production rate increased to around 30 kilograms per s. These kinds of measurements imply that its coma was not just a weak occasional puff, but a relatively steady release of dust over time as it warmed. From those observations, some scientists conclude that 3I/Atlas turned on around 6 to 9 AU from the Sun. That's far compared to many solar system comets, which often show only weak to no activity until they come inside of 3 to 5 AU, depending on how volatile their ices are. The early activity indicates that 3I/Atlas contains volatiles that sublimate at lower solar heating. Another implication is that the surface or near-surface layers are not so thick or insulating that heating cannot reach volatile ices. If the surface were heavily covered by dust or some kind of insulating crust, then heat from sunlight might not penetrate enough to release gases or dust at large heliocentric distances. The fact that activity is already happening suggests that either the surface is relatively fresh or permeable, or that volatiles are closer to the surface. Some comets only become visibly active when they cross inside the orbit of Jupiter, or even closer to the Sun. But 3I/Atlas appears to be active much earlier. Also, its brightening law, how brightness increases versus distance, is steeper than for many comets, unless those comets are dynamically old or have already had changes that expose volatiles. At the same time, in data from 2024 when 3I/Atlas was still much farther, ranging about 13 to 17 AU, no strong outbursts or obvious activity was seen above what might be expected for a bare nucleus or very low activity. That suggests that while activity begins at some distance, it may remain weak until certain thresholds of heating or sunlight angle are met. Because these pre-discovery images go back months before formal discovery, they give a longer baseline for seeing how 3I/Atlas evolved as it approached the Sun. They let astronomers trace the light curve, compare how dust production increased, and check whether spectral or color changes happened gradually or in steps. All that provides insight into internal structure. One question is whether there was distant activity, meaning gas-dust release when solar heating is weak. The test data and ZTF data both support that yes, there was modest activity already, meaning 3I/Atlas has some volatiles that are volatile enough to react even at low flux of sunlight. These early activity behaviors do more than just confirm that 3I/Atlas is active. They suggest that its internal structure may be conducive to early sublimation. It may also have cracks allowing sun heat to reach inside. These are similar to what some solar system comets show, but many comets are covered by insulating layers of dust or organics that delay their activation until closer to the Sun. Learning the exact dynamics of interstellar comet outgassing might be a key factor in designing missions to physically intercept these bodies for detailed study. Hypervelocity and stardust, tracing Atlas's motion across the galaxy. When 3I/Atlas was discovered, one of the first figures astronomers reported was its excess velocity relative to the Sun. This is often called V infinity, the speed the object has when it is far from the Sun, once the Sun's gravity no longer pulls significantly on it. For 3I/Atlas, that speed is about 58 km per s relative to the Sun. A higher V infinity implies a few things. First, it suggests Atlas may be older, or at least that it has had more time since ejection from its home system, because over long times, gravitational interactions in the galaxy with other stars, molecular clouds, galactic tides, tend to mix velocities and increase random motion. In formal studies, astronomers use relations between stellar ages and velocity dispersion to infer possible age ranges. The faster something moves relative to average motion, often the more time it might have been drifting. In the case of Atlas, one study estimates its age at somewhere between 3 to 11 billion years, under the assumption that the object's velocity dispersion is similar to that of stars. That is, it could be very old, possibly formed nearly as long ago as many of the stars in our galaxy. Where might Atlas have come from? Because of its speed and trajectory, some astronomers suggest it may have originated from what's called the galactic thick disk population. The thin disk is where most of the young and middle-aged stars are, including the Sun, and these stars tend to have lower relative velocities. They move more in flat orbits around the galaxy, closer to the galactic plane. The thick disk has older stars, whose orbits are more tilted or have larger vertical excursions, meaning they move above and below the galactic plane more and typically show larger random motion. Because Atlas shows a high excess velocity and certain components of motion, it may be consistent with being born in a thick disk star system, or at least coming from such a population. Astronomers also examine how far Atlas deviates from the galactic plane over time, and how its orbit through the galaxy behaves if traced backwards. In one work, The vertical excursion is larger than for many nearby stars. That too suggests origin in an older population of stars. Another question is whether Atlas was ejected recently from its home system or long ago. The speed alone doesn't tell exactly when, but it gives clues. If ejection were recent, say a few million years, then it should probably have a lower drift in velocity relative to local stars, and its orbit trace back might point to a relatively nearby star. But searches for candidate stars that Atlas might have passed close to over recent time, say in the past 10 million years, have so far found none that can be clearly tied to being its source. One recent study looked into Gaia DR 3-star catalogue for potential close encounters, but found no star within a few parsecs in recent time that would change Atlas's velocity much or serve as its birth system. Galactic gravitational perturbations over a long time are important. Passing stars, encounters with molecular clouds, and the general gravitational potential of the Milky Way can change or stir the orbits of small objects. These perturbations can alter velocity direction, impart small impulses, and change the orbit shape. For Atlas, because its velocity is high and its orbit already hyperbolic with respect to the Sun, these perturbations matter more in understanding where it came from, rather than how Atlas is bound to the Sun. But models show that over billions of years, Atlas's velocity vector would have been modified several times, making precise origin tracing difficult. Oumuamua's lower excess velocity of 26 km/s means it was moving more similarly to local stars and had less random motion. This suggests it may have been ejected more recently, or at least that its velocity drift has been less, or that it comes from a region of the galaxy with less stirring. Borisov, with about 32 km/s excess velocity, is higher than Oumuamua, but still well below Atlas. Its trajectory likewise is consistent with some older drift, but not as extreme. So Atlas stands out. It is the fastest interstellar object we have observed coming into the solar system. That suggests a longer journey, more wandering through the galaxy, and more exposure to whatever effects happen in interstellar space. What else does a high speed imply? Because it is moving so fast relative to the Sun, the heating from sunlight as it approaches will rise more rapidly than for slower objects. It passes through more of the Sun's sphere of influence quickly. This means that thermal lag may reduce or delay some parts of its activity. Also, gas and dust released will have less time to accelerate or escape before conditions change, possibly affecting how the coma develops. The solar system itself orbits the center of the Milky Way at about 220 to 240 km/s, and the Sun has some peculiar motion relative to average stars. Interstellar objects' velocities are measured relative to the Sun, but to understand where they likely came from, astronomers transform those velocities into galactic coordinate systems using U, V, W components and compare with local standard of rest and with the velocity dispersions of stars of different ages. In Atlas's case, its UV-W components are large in magnitude in certain axes, consistent with old populations. The fact that no clear stellar source has been found supports the idea of long drift. Atlas's speed also means its journey through the galaxy and its interstellar life have likely left imprints. Surface alteration, volatile depletion, craterization, or cosmic ray processing may be deep. As more observations sharpen its motion and spectral fingerprints, astronomers hope to better narrow its source and use Atlas as a probe of the history of the galaxy's small icy bodies. How many have been ejected? How many survive? And what their journeys do to their structure and materials. The threat question: could Atlas hit Earth, the Moon, or Mars? Any object entering the solar system from outside, especially on a hyperbolic trajectory, raises the question, could it collide with something? Scientists moved quickly to work out the full orbit and use the best observations to see how close it will get and with what uncertainty. From careful tracking and precovery images, astronomers refined 3I/Atlas's orbit well enough to know several key distances: its closest approach to the Earth, to Mars, and to the Sun. According to NASA and ESA estimates, 3I/Atlas will not come closer than about 1.6 to 1.8 AU from Earth, which is about 240 to 270 million. Specifically, its closest approach to Earth is expected on the 19th of December 2025, at about 1.8 AU from Earth. That distance is far larger than Earth's orbit radius, meaning Atlas will be well outside Earth's immediate neighborhood. It will approach Mars more closely, around 0.19 AU, or 30 million kilometers, on the 3rd of October 2025. Even that is a safe distance in cosmic terms, though much closer than its approach to Earth. Its perihelion, or closest distance to the Sun, will be about 1.36 AU, happening on the 29th of October 2025. That lies between the orbits of Earth and Mars. So from the numbers, it's clear Atlas will not cross Earth's orbit in a way that could endanger Earth or the Moon. Its path brings it inside Mars's orbit, but not Earth's. Because of its tilt and its large excess velocity, its path doesn't intersect with Earth in a dangerous way. Why those early worrying diagrams or speculative questions are misleading comes down to uncertainty, observation time, and orbital mechanics. When an object is first discovered, its path is only weakly constrained. In such cases, diagrams sometimes show a broad envelope of possible paths, some of which might appear to pass near Earth. But as more observations are made, precovery images, follow-ups, that envelope narrows greatly. For Atlas, enough observations and precovery data have allowed scientists to reduce uncertainties, so that all modeled paths avoid Earth by a large margin. Because Atlas is on a hyperbolic trajectory, it is only passing through. Its speed and inclination make it unlikely to have close encounters unless by coincidence. The gravitational forces of the Sun and the planets will bend its path slightly, but not enough to bring it to Earth. Also, Earth and the Moon are tiny targets compared to the scale of Atlas's path through space. At the time of its closest approach to Earth, Atlas will be behind or near the Sun from Earth's point of view, making it very hard to observe. The geometry means even though Earth will be closer in some sense, the line of sight is blocked or near the Sun's glare. Near Earth, objects, or NEOs, are classified and their impact probabilities are calculated via the Torino scale or Palermo scale. If an object is predicted to cross Earth's orbit and comes within a certain distance with some uncertainty, then risk steps are taken. But with Atlas, it was never classified a NEO in the sense used for impact threat, because its orbit and distance clearly keep it well outside the danger zone. ESA, NASA, and other agencies have stated explicitly that Atlas poses no threat to Earth. Even for Mars, which Atlas will approach more closely, 0.19 AU is large, so there's no risk to Mars either. No body of size like Atlas is predicted to intersect Mars directly. What about the Moon? The Moon orbits Earth, so if Atlas is far from Earth, it's nowhere near the Moon either. The Moon's orbit is only about 384,000 kilometers from Earth, which is tiny compared to hundreds of millions of kilometers. So Moon impact is equally impossible. Could debris or tail dust pose any risk? Even though comets shed gas, dust, ice, those particles disperse quickly, are small, and dilute over vast volumes. There's no known mechanism or density of debris from Atlas that would create an effect near Earth or satellites. Energy and damage. What if Atlas struck Earth? But what would happen if Atlas were to strike Earth? Estimates for its nucleus diameter suggest a range somewhere between under 1 kilometer and up to 5 to 6 kilometers in diameter. The speed with which it's moving as it enters the Sun's influence is about 58 kilometers per s. With those numbers, one can roughly estimate the kinetic energy it would carry if it hit Earth. The impact energy would be on the order of several million megatons of TNT if a 3 kilometers nucleus at 58 kilometers per s hit intact. That is enormously larger than anything in recorded human history. For comparison, the Tunguska event of 1908 is estimated at between 5 and 15 megatons of TNT. The Chelyabinsk meteor of 2013 released around 0.5 megatons in its airburst over Russia. What kinds of effects might that produce given such energy? The answer depends heavily on whether the nucleus remained intact on entry or broke apart, what angle it entered, how much of its mass got to lower atmosphere or surface, composition, ice fraction versus rock, and how much of the energy is dissipated high up versus deep. For large, loosely held bodies, much of the body might disintegrate or explode in the upper atmosphere, creating a massive airburst. If the body is more solid or metal-rich, more of it might reach the ground, forming a crater. An object several kilometers across, moving so fast, would cause devastation over wide regions. If it hit land, the shockwave, heat and ejecta would obliterate tens to hundreds of kilometers radius. Incineration close to impact, fires, earthquakes, massive dust thrown into atmosphere. A huge impact like that would push dust, water vapor, possibly ice, into the stratosphere. Global cooling might result for months or even years depending on how much material is injected, how reflective it is, etc. If an intact core struck Earth, a very large crater, kilometers wide, tens of kilometers across, would form along with melt, vaporization and ejecta distributed widely. If the nucleus broke apart before or during atmospheric entry, multiple fragments or a swarm could reach Earth. Smaller pieces might burn in the atmosphere, producing multiple shockwaves, meteorite fragments, perhaps impactors on the ground. Effects would be more localized but still intense. Because Atlas is likely composed significantly of ice, volatile material, the body might break up high in the atmosphere, reducing surface damage but increasing atmospheric effects like heat, pressure wave, and perhaps severe air blast damage over a wide area. Similar to Tunguska, but on a much larger scale. A 100M body, like Tunguska scale, produces tilde 515 megatons on airburst. A 1 kilometer body might produce energies in the range of tens to hundreds of thousands of megatons, depending on speed and composition. A 3 kilometers body at 58 kilometers per s, as in our rough estimate, would be much larger, possibly several million megatons, so orders of magnitude worse. It would almost certainly be globally catastrophic. Climate effects, disruption of agriculture, huge fires, maybe mass extinction depending on the exact scenario. Even a fragment or partial core might destroy large regions, possibly a whole country-sized region, depending on where it hits and secondary effects such as tsunamis. If impact is in the ocean, the tsunamis could be enormous, depending on size, depth and location. If the impact is on land, ejecta, dust, molten rocks, shock waves, fireballs and blast waves would obliterate everything within tens to hundreds of kilometers, possibly more. Thinking through this hypothetical very quickly helps illustrate why astronomers are so quick to measure size, speed, composition, and orbit of any large body that could potentially come close to Earth. The risk of damage is far too severe to be taken lightly. What we learned wrong from Oumuamua, updated biases and misinterpretations. We learn a lot by seeing where earlier assumptions about Oumuamua turned out to be wrong, or at least incomplete. The story of Atlas gives scientists a chance to correct biases and refine ideas about what interstellar objects can look like, and why caution is needed when drawing conclusions from limited data. When Oumuamua was discovered in 2017, some of the first assumptions were that lack of a visible coma meant it was probably an asteroid or rocky body rather than a comet. Because telescopes saw no tail or gas emission, many assumed it had no volatile ices, or that any ice was buried beneath a crust. Also, its strong brightness fluctuations led to inferences that it had a very elongated shape, maybe cigar-like or pancake-like. Many models built from limited brightness data, assuming simple reflection and rotation, treated those light curves as showing a nucleus shape directly. Some hypotheses assumed that its unexpected acceleration had to come from outgassing, but without direct detection of gas, that remained speculative. Others proposed more exotic ideas, hydrogen ice, nitrogen icebergs, or even non-natural explanations. These assumptions, while imaginative, turned out to rest on thin observational ground. Good science did explore them, but many turned out to be too little evidence to settle the question. Atlas helps show where some of these assumptions need revising. One bias from Oumuamua was that absence of observable coma meant absence of volatiles or activity. But Atlas was seen to have coma and tail even when far from the Sun, showing that strong volatile activity can begin earlier, and that coma signatures can be faint or delayed depending on surface insulation, particle size, reflectivity, and observer sensitivity. Atlas's high CO2 to H2O ratio, early activation and dust production suggest that a body can appear inactive in certain observations, yet still carry lots of volatile icy material, challenging the idea that Oumuamua's lack of observed outgassing meant it was dry or inert. Another correction comes in interpreting light curves and shape from brightness variation. With Oumuamua, large amplitude in brightness changes was taken as evidence for extreme elongation. But large amplitude can also stem from shape plus non-uniform surface reflectivity, dust jets, rotational tumbling, or orientation effects, how we see the object, whether pole on, edge on, etc. Atlas's light curve shows modest brightness variation, and because its coma contributes so much light, much of the nucleus's shape is masked. That means brightness variation underestimates elongation or may mislead. Seeing how Atlas behaves as its coma thickens, whether amplitude drops, will refine how we interpret light curves from interstellar objects in general. A third bias was in interpreting trajectory or speed anomalies. In Oumuamua's case, its observed non-gravitational acceleration was taken by many to be caused by cometary outgassing. But without direct detection of gas, that hypothesis had to lean on indirect inference. Some assumptions about surface composition were brought in to try to explain what drives that acceleration. Atlas, with its strong spectroscopic detections of CO2, carbon monoxide, water, dust, etc., gives an object where gas sublimation is directly observed, so models that invoke outgassing become more grounded. That helps scientists test, for future objects, whether acceleration can be cleanly tied to observed volatile emission, or whether additional forces are needed. Because of Oumuamua's strangeness, some models assumed that interstellar objects might be mostly inert, rocky fragments rather than icy comets. Atlas's early activation, its visible coma and tail, and its volatile richness suggest that many interstellar objects could in fact be more like comets than asteroids, and that earlier surveys may have missed many because they were looking for objects that matched comet-like descriptions only once close to the Sun. The detection bias of surveys being more sensitive to certain kinds of activity or brightness becomes more obvious in light of Atlas. Objects with activity far from the Sun, or faint comas, or dominated by CO2 rather than water, may have been undercounted or misclassified. There was also an assumption that when light curves show large brightness variation, one can deduce nucleus shape cleanly. But with Oumuamua, variability could be, and likely was, influenced by orientation, albedo variation, or even surface features, not just pure shape. The assumption that shape is extreme may have been overinterpreted. Atlas's more modest variability, plus its dusty coma, show that shape inference must be done more carefully. Finally, another wrong idea was that Oumuamua might represent typical interstellar visitors. Early after its detection, many asked whether all interstellar objects would look like that. But Borisov showed a more normal comet. Now, Atlas shows further normalcy mixed with some strangeness. It behaves like a comet in many ways, but has unusual chemistry or velocity. This mix means that assumptions based only on Oumuamua would miss much of the diversity possible in interstellar objects. Because of these lessons, scientists today remain cautious. They now expect that future interstellar objects might show combinations of traits. Some very comet-like, some more inert, some with high volatile content, some depleted, some with extreme or irregular shapes, some more regular, some traveling very fast or from odd directions. Atlas underscores the value of precovery images, multi-wavelength spectroscopy, frequent monitoring to catch early activity, and careful disentangling of nucleus versus coma light. The case of Oumuamua taught us that in sparse data, It is easy to misinterpret absence of evidence as evidence of absence or infoshape or composition beyond what light curve, color, and orbit alone can support. With Atlas, many of those earlier missteps are being corrected or at least tempered, and the result is a more nuanced science of interstellar visitors. Extraterrestrial or natural, the debate over artificial versus natural origins. Some people, most notably Avi Loeb of Harvard and others associated with the Galileo project, have raised the possibility that Atlas might be artificial. Their arguments focus on a few unusual features. One is the trajectory and speed. Some suggest that if an object has an especially fine-tuned trajectory, or seems to avoid the kinds of scattering or random perturbations expected for dusty comets over a long time, that could hint at some design or guidance rather than purely random motion. Another argument points to how reflectivity and brightness behave. If Atlas had unusually reflective surfaces, sharp or engineered materials shine, or showed unexpected changes in brightness or behavior unexplained by outgassing or dust emission alone, those might be considered clues of artificial origins. Some speculative hypotheses suggest that if Atlas performs deep space maneuvers or emits signals or radiation not typical for comets, these would also be signs of something non-natural. Proponents of artificial origin argue that we should not dismiss these possibilities because, after all, interstellar objects are rare and many features are unprecedented. So being open to alternative hypotheses helps push observation and data gathering. However, the bulk of the scientific community finds that the evidence strongly supports a natural origin for Atlas and argues that many of the odd properties can be explained by known natural mechanisms. The first counter-argument is that Atlas shows cometary features that match what comets do when warmed. These are signatures of natural processes. NASA scientists have said that Atlas behaves like a comet in just about every way, and that the best evidence overwhelmingly supports it being a natural body. Another counter is that trajectory oddities or high speed are not sufficient to imply artificiality. Many interstellar objects are expected to come in at relatively high speeds because of the dynamics of star systems, stellar motion, gravitational interactions, etc. Random motion, encounters with stars or molecular clouds and long drift through the galaxy can produce high speed and somewhat unusual orbits without design. Also, reflectivity or unusual brightness might result from volatile composition or surface features rather than engineered materials. A further argument against the artificial hypothesis is the lack of independent evidence for anything like engineered signals, alien transmissions, or any marker of intelligent manufacture. All observations so far are compatible with natural comet models. The behavior of the coma, spectroscopic detections of volatile gases and dust all match what comets sometimes do, especially those with abundant CO2, volatile content, or surfaces subject to volatile layering. Scientists tend to apply Occam's razor. The simplest explanation that fits the data is preferred unless there's strong conflicting evidence. NASA, for example, has explicitly dismissed artificial origin claims for Atlas, saying the evidence points to comet-like behavior. One of the speculative claims is that since Atlas's tail doesn't show, or hadn't shown in early times, that could, they argued, point towards something artificial. But natural comets vary. Comets far from the Sun often have weak or undetectable visible tails until volatile sublimation gets strong, or until sunlight is intense enough. CO2 or carbon monoxide-driven activity sometimes produces coma without visible tails initially. So lack of a strong visible tail early on is not unusual enough to claim artificial origin. In many telescopic observations, what looks shiny or unusually bright is instead consistent with reflective ice, dust or small particles, or with grains exposed by outgassing or small fresh surfaces. The spectra from JWST and others show heavy CO2, water vapor, dust and ice, matching natural comet chemistry rather than anything clearly artificial. Science tries to stay tethered to evidence. Observational data are collected, models are built, hypotheses are tested. Claims of artificial origin usually are flagged as speculative, what-if scenarios rather than accepted interpretations. For example, Avi Loeb has written that the simplest hypothesis is that Atlas is a natural comet and that alternative ideas are being floated to motivate data collection rather than because they are strongly supported. In one case, a claim was made saying Atlas does not exhibit a strong comet tail or plasma, dust emissions typical of many comets, and that its trajectory is unorthodox. And from this, that artificial origin should be considered. But NASA responded emphasizing that any anomalies observed are not outside the range of natural comet variation. In short, the debate reflects a tension. On one hand, honesty in science demands we consider all possibilities. On the other hand, extraordinary claims require extraordinary evidence. Atlas has many things that are unusual, but so far nothing that clearly breaks what is natural for comets or interstellar objects. Unless future observations show something like engineered signals, impossible material properties, or behavior that resists all natural explanation, the consensus is that Atlas is a natural object. Weaponizing fear, media, public perception, and scientific caution. There's a lot to say about how media, public perception, and science interact when it comes to objects like 3I/Atlas. The way uncertainty works, the way scientists speak in cautious tones, and the way headlines scream danger. All of this shapes how people think about interstellar visitors. Atlas offers a useful case study in how fear gets weaponized, intentionally or not, and how scientific caution both helps and suffers in the mess. First, there are many media stories that exaggerate or stretch possibilities. Some headlines present Atlas as if it might hit Earth, or that it might be alien technology, or that it's a spaceship rather than a comet. For example, Fox News ran a story quoting Avi Loeb saying Atlas could be a nuclear-powered spaceship. Another article suggested the object had turned green or something has been switched on as it neared the sun, with hints of sensationalism. Some publications use dramatic graphics or imagery, bright comet tails, Earth looming in the background, to evoke worry even when the scientific consensus is that Atlas poses no threat. On the other hand, the scientific statements are much more reserved. NASA's fact pages clarify very early that Atlas is classified as interstellar because of its hyperbolic orbit, that its orbit does not cross Earth's path, and that it will never come closer than about 1.8 AU to Earth. Scientists also emphasize that, while it is mysterious and interesting, its behavior is consistent with cometary physics in many respects. In the Debrief article, NASA's Tom Statler is quoted, "It behaves like a comet. Evidence is overwhelmingly pointing to this object being a natural body." The uncertainty inherent in early observations tends to breed sensationalism. When data are sparse, several models are plausible. Some media will take one speculative possibility and present it as if it is very likely. For instance, Avi Loeb has put forward the possibility of an anti-tail for Atlas, which is unusual, though he also acknowledges that natural models can explain it. Some media pick up the speculation but omit the caveats, which creates misleading impressions. There have been fact checks such as, "Scientists did not agree that 3I/Atlas is alien spacecraft," which point out the exaggerated claims. Public reaction feeds on headlines. When people read that a physicist says it could be a spaceship or nuclear-powered probe, curiosity and concern spread. Social media amplifies the most ominous possibility. Fear sells, in a sense, but that can distort scientific understanding. People may think risk is higher than it really is. Scientists often have to respond not just to data, but to public misperception, which can take time and attention away from pure research. The effect of this dynamic is double-edged. On one side, sensationalism increases attention, which can lead to more funding, more telescopes pointed, more data gathered. Because of high public interest, projects receive support. That can be good. More observations mean better science. On the other side, it can push scientists or institutions to respond faster, perhaps overstate certainty, or avoid raising less dramatic possibilities. Also, if public fear grows too much, policymakers might demand safety assurances or restrictions that are unnecessary, which can misallocate resources. Scientists try to manage this by being explicit about what is known versus what isn't. When NASA says Atlas poses no threat, it does so in its official science pages. When Avi Loeb suggests speculative ideas, he generally frames them with disclaimers. Cannot be ruled out, but requires better evidence. In the Fox News story, he says natural models fail to explain some oddities, but does not claim artificial origin definitively. This is typical. Science works with probabilities, not certainties, especially early in study. The contrast between scientific caution and headline risk is stark. For example, while NASA and observatories say no threat, some media reports ask, could Atlas hit us? Or alien probe headlines. Those are questions, but often leave out that the scientific estimates have already ruled out Earth impact. That mismatch leads to confusion. Readers may see sensational headlines and assume scientists are worried even when they are nearly certain there's no danger. There are some consequences. Public fear can push funding toward planetary defense and detection systems, which might be good. But it can also lead to clickbait science, where discoveries are hyped for public engagement rather than careful disclosure. Sometimes, scientists may feel pressure to issue strong statements to reassure, which could oversimplify complexity. In education, public trust in scientific institutions can suffer if people feel they were misled by earlier sensational stories. Policy can be influenced. If the public demands safety, governments may allocate resources to monitoring interstellar objects or more telescopes, which in some cases is useful. But sometimes decisions are made under pressure rather than from scientific priority, which could divert resources from other needed work, such as asteroid detection, climate monitoring, etc. There is also risk that misperceived danger could lead to anxiety, misinformation, or conspiracy theories. Agencies often publish FAQs, risk charts, and clear data on orbits to counter exaggeration. NASA's Comet 3I/Atlas page includes clear statements of closest approach. Public media statements from observatories or scientists sometimes note what could go wrong, but emphasize what currently is known. The idea is to maintain credibility. Overhyping and then being wrong damages trust more than being cautious. Atlas's story shows how the combination of uncertainty, human curiosity, and media incentives can lead to heightened fear, often beyond what scientific evidence warrants. But it also shows that science has built mechanisms, peer review, official statements, measured language, to respond and correct misunderstandings. Observing this interplay helps us see that with rare, strange cosmic visitors, it is not only what is discovered, but how it is communicated that shapes how people respond. Policy and precaution. If an object isn't entirely natural. If the possibility arose that an interstellar object like Atlas was not entirely natural, the shift in scientific, political, and ethical thinking would be immediate and profound. For decades, astronomers have operated under the assumption that every comet, asteroid, or rogue visitor from interstellar space is a chunk of rock or ice formed in a planetary system and flung outward by chance. But should even a hint of artificiality appear, be it in the form of regular geometric shapes, unusual reflective patterns, anomalous accelerations not explained by outgassing, or even embedded materials inconsistent with natural processes, the question of how to treat the object would no longer be limited to astrophysics. It would become an issue of planetary defense, international law, public trust, and even humanity's philosophical self-understanding. The fact that Oumuamua already sparked speculative claims of artificial origin shows how quickly the debate could ignite when anomalies appear. The first matter to confront would be planetary protection. Up until now, guidelines in this area have been shaped largely by robotic missions to Mars, Europa, or comets within our solar system. The Committee on Space Research has established protocols designed to prevent contamination in both directions. We must avoid bringing Earth microbes to alien environments that might harbor life, and equally avoid bringing unknown life or chemistry back to Earth. But those rules were written in the context of known solar system bodies. None of them were designed for an object that has traveled between stars and could, in theory, carry signatures of a completely different biosphere. If an interstellar body contained microbes, spores, or exotic biochemical structures, the risk of forward contamination, us damaging what might be the only evidence of a non-terrestrial biology, would be significant. At the same time, back contamination would be far more frightening, since humanity has no experience with non-Earth biology and no defenses against it. Even if the probability were extremely low, the consequence of being wrong could be catastrophic. For this reason, any physical interaction, whether sampling the surface or returning material, would demand a far stricter biosafety regime than what is currently used for Mars missions. The issue would not stop at biology. What if the object contained hazardous materials of non-biological origin? Some interstellar bodies might, hypothetically, carry unstable isotopes, high concentrations of heavy metals, or even artificial substances unknown in nature. If fragments were brought to Earth without precautions, they could pose radiological, toxicological, or chemical risks. If artificial alloys or engineered nanostructures were detected, the stakes would escalate again because those would strongly imply intelligent origin. At that point, governments would almost certainly step in, both to manage the danger and to control access to what could be revolutionary technology. This creates a tension. Should such knowledge be treated as the property of all humankind, as international treaties like the Outer Space Treaty might suggest? Or should it be restricted for reasons of national security and technological advantage? History suggests that secrecy would win, at least in the short term, but the scientific community would push back, arguing that such a find belongs to everyone. Ownership, sovereignty, and legal frameworks would therefore become a central concern. The Outer Space Treaty prohibits nations from claiming celestial bodies, but it does not clearly cover transient objects passing through our solar system. If an interstellar probe were found, who would have the right to approach it, study it, or even attempt recovery? Would it be considered a common heritage of humanity, like the deep seabed, or would it fall under a first to reach it, first to study it principle? The problem grows more acute if the object turned out to be an active probe. In that case, interference might be seen as tampering with another civilization's property, raising questions that international law has never had to address. The detection of an interstellar visitor is always global because astronomers from multiple countries contribute observations. But the decision to act, whether by launching a mission or announcing a discovery, usually lies with the handful of nations and agencies that have spacefaring capability. NASA, ESA, Roscosmos, CNSA, ISRO and JAXA would all have claims of interest, but they also operate in a world of geopolitical competition. The temptation for one actor to move ahead without waiting for global consensus would be strong. A private company such as SpaceX or Blue Origin could further complicate matters by launching its own mission to intercept the object, acting independently of governments. Such actions might generate conflict if they appeared reckless, or if they deprived the world of a shared scientific opportunity. For this reason, many scientists argue that humanity should establish an international framework now, before the next such discovery, to avoid chaos when the stakes are highest. But suppose the evidence of artificiality was ambiguous rather than definitive. This grey zone scenario might in fact be the most likely, since nature often produces oddities that don't fit neatly into existing models. Imagine an object whose acceleration could not be fully explained by outgassing, whose reflectivity suggested metallic patches, or whose shape was unusually regular. Would that be enough to trigger claims of intelligence? Some scientists argue that the burden of proof should not automatically exclude artificial explanations, since refusing to consider them risks missing the most important discovery in history. Others argue that unless definitive proof, such as engineered materials or coded signals, were found, speculation would remain premature. The risk of false positives is enormous. If the scientific community cried alien probe and was later proven wrong, credibility could be damaged for generations. At the same time, waiting for unambiguous proof might mean missing the chance to study something truly unique before it left the solar system forever. Standards for scientific claims therefore matter greatly. Robust protocols for data handling, peer review, and independent verification would be essential to avoid rushing to conclusions. Just as with fast radio bursts, which were once thought by some to be possible alien signals, but are now largely understood as astrophysical phenomena, interstellar objects demand caution. If artificiality is even hinted at, data must be shared quickly across the global community so that no single group controls the narrative. The risk is that secrecy or selective reporting could amplify conspiracy theories, erode public trust, and undermine whatever scientific value the discovery holds. How humanity should respond if an interstellar object were found to be an intentional probe? Should we attempt communication, interpreting its arrival as an invitation? Or should we remain silent, treating it as an observation platform that we should not disturb? Advocates of messaging extraterrestrial intelligence, or METI, would argue that active outreach is the logical next step, while others caution that advertising our presence carries unknown risks. It is also possible that the probe would be ancient, derelict, or no longer in contact with its makers, in which case any attempt at communication would be futile. Still, the mere presence of such a device would raise questions about our place in the galaxy, about whether other civilizations are common, and about how humanity should present itself if contact is ever made. Religious, cultural, and philosophical dimensions cannot be ignored either. Some communities would interpret the discovery as confirmation of long-held beliefs about other intelligences in the universe, while others might see it as a threat to human uniqueness. Governments would need to manage not only the technical and security aspects, but also the public reaction, which could range from excitement to fear. Transparency would be key, but transparency is often difficult when national security and prestige are at stake. Human history is filled with cases where exploration led to unintended consequences: species extinction, the spread of disease, destruction of cultural artifacts. With interstellar objects, the stakes are higher still because the material could represent not just another world's biology or geology, but possibly another world's technology. The choice to touch, sample, or alter such an object is not merely a scientific decision. It is a decision about how humanity treats what may be the first direct encounter with the wider galaxy. Move too quickly, and we could destroy irreplaceable evidence. Move too slowly, and we might let history slip past us without seizing the opportunity. Tools of discovery: surveys, telescopes, and sky scanners. The discovery of 3I/Atlas has shown just how strong modern survey telescopes and space instruments have become. Several tools, sky scanners, wide-field surveys, space telescopes, and clever analysis methods, work together to catch Atlas early, follow it well, and measure many of its oddities. Understanding what each instrument can do helps us see how interstellar objects are finally coming into view more reliably, and how improvements are pushing detection thresholds lower. One of the central tools in discovering Atlas was the Atlas survey. Atlas is not just one telescope, but a global network of 4 telescopes, 2 in Hawaii, 1 in Chile, and 1 in South Africa, with cameras that scan large parts of the sky each night. These telescopes have wide fields of view, each pointing covers several degrees of sky, and they are automated to take repeated images of each patch, looking for moving points of light. Atlas can scan the whole visible sky from each location roughly once per night, reaching down to a magnitude around 19 under good conditions. The system's design, global spread, wide field, repeated imaging, makes it well suited to catch fast-moving or faint objects like interstellar visitors. Another key tool is the Zwicky Transient Facility in California. ZTF uses a 1.2-meter Schmidt telescope at Palomar Observatory with a huge camera covering about 47 square degrees of sky in each exposure. It scans the northern sky every 2 or 3 nights, operating in optical bands to pick up transient objects. Because of its large area and frequent revisits, ZTF can catch objects early, even when they are faint, or recover images of them later. For Atlas, ZTF provided many such archival images that helped refine its path, brightness, evolution, and activity far before its discovery. Space-based tools are also crucial. TESS, primarily designed to find exoplanets by observing dips in star brightness, turned out to be useful for Atlas too. TESS observed the region of sky containing Atlas from early May to early June 2025, before Atlas was formally discovered, generating continuous coverage. While Atlas was too faint in individual exposures, scientists used image stacking to recover detections of Atlas well before discovery. That extended the observation baseline, allowed better estimates of brightness, and offered warning that activity was occurring when the object was still far from the Sun. Then there are powerful space telescopes like the Hubble Space Telescope and JWST. Hubble provided sharp images of Atlas when it was still distant, making it possible to constrain nucleus size by resolving finer structure in the coma and seeing the dust plume off the Sun-facing side. From Hubble we learned that the nucleus cannot be larger than a few kilometers, but could be much smaller, given how much dust is around it. JWST, particularly with its NASPEC instrument, brought strong spectroscopic power, catching infrared signatures of gases, ices, dust, and determining that the coma is CO2-rich, showing other volatile molecules, water ice grains, etc. The sensitivity of JWST to faint gas lines and wide wavelength coverage means it can detect small amounts of gas that ground telescopes might miss. Ground-based large telescopes also play a part. Gemini South, the Very Large Telescope, and observatories in Chile, Hawaii, etc. help with follow-up imaging and spectroscopy once something like Atlas has been flagged by surveys. These telescopes tend to have larger mirrors, 4-10 meters or more, which collect more light, letting scientists see fainter details, finer dust tails, shape of coma, small spectral features, even polarization measurements, which give clues to dust particle size and composition. Once Atlas was identified, astronomers went through images taken previously by Atlas units, ZTF, TESS, maybe others, to find pre-discovery observations. Those earlier images let scientists extend the observation arc backward in time, refine the orbit more precisely, see how brightness was changing earlier, detect activity earlier, estimate when dust emission started. Without archival data, the uncertainty in orbit, in velocity, in brightness evolution would be much larger. Image stacking helps raise the signal of faint moving objects. Careful calibration of background stars, careful modeling of the motion, use of multiple filters or infrared bands, all help distinguish moving faint cometary objects from background noise. Use of a wide field of view with frequent revisits means surveys don't miss fast movers or dusty objects that are faint and show little activity early. The sensitivity of instruments is increasing over time. Cameras with more pixels, better pixel scale, lower noise, better filters for separating comet light versus sky background, better software for automatic detection, better algorithms for filtering moving objects, etc. All contribute. For example, Atlas's telescopes with 0.5 meter Schmidt-type instruments, wide field, fast readout, automatic detection pipelines paired globally allow near-nightly coverage in many parts of the sky. ZTF similarly uses large field and fast cadences. Space telescopes like JWST bring sensitivity to faint gases and small spectral lines. All of this makes detection thresholds steadily lower. Future surveys promise even more. The Vera Rubin Observatory is expected to cover almost the entire sky frequently with deep sensitivity, which could find many more interstellar objects, perhaps ones even smaller, fainter and more distant from the Sun. Some of its operations may already be capturing Atlas images and will help future ones. Also, improvements in infrared and all-sky surveys enhance ability to see volatile activity before brightness from dust dominates. So, Atlas is a product of this growing toolbox. These tools, working together, are lowering detection thresholds so that previously invisible visitors, faint, small, or far out, can now be spotted earlier and studied in greater detail. Potential missions. Could we catch Atlas in flight? Catching a fast interstellar visitor like 3i/Atlas reads like a thriller. The phone rings, People point telescopes and suddenly the clock starts ticking. In practice, the physics of catching something that is already inbound at tens of kilometers per second makes the idea brutally hard. The object's orbit and its incoming excess speed relative to the Sun is very large, so any spacecraft launched from Earth after discovery faces a huge energy gap, or delta V, to match course and speed. That gap is the main practical reason why a direct post-discovery intercept is almost always out of reach for current rockets. Why the delta V matters so much can be explained without equations. A spacecraft already in Earth orbit has a certain orbital speed. To catch Atlas, you either accelerate the spacecraft to raise its orbit and meet the comet, or you change the spacecraft's path so the Sun bends it toward the comet, or do both. Increasing a spacecraft's speed by a few kilometers per second is doable with big rockets. Increasing it by tens of kilometers per second is not, at least not with chemical rockets on a reasonable budget. That is why most serious studies say a post-discovery straight-out launch to intercept Atlas is not feasible with current launchers and propulsion systems unless the detection comes very early and the launch can exploit favorable geometry. How have people thought about similar problems before? The Project Lyra team studied how one might chase Oumuamua and explored options ranging from massive rockets plus gravity assists to exotic ideas like solar obverse maneuvers or beamed sails. Project Lyra showed that catching a fast interstellar object is possible in theory, but typically requires either huge delta V budgets, carefully timed gravity assists, or creative high-energy maneuvers near the Sun to grab extra speed. Those papers are full of numbers, but the practical takeaway was simple. You can reach an interstellar object, but you need a lot of energy, very favorable timing, or advanced propulsion. Agencies have also developed a different kind of strategy. Be ready in advance. ESA's Comet Interceptor is the leading example. It will park at Sun-Earth L2, carrying 3 small spacecraft ready to swing out to a newly discovered long-period comet or interstellar visitor. That mission is built for surprise targets. It is pre-launched and waiting, so it avoids the impossible rush of a post-discovery launch. A ready, waiting interceptor can make a close flyby with reasonable delta V and deliver high science return exactly because it is already in space. That idea is why many scientists now argue we should focus on ready missions rather than chasing visitors from the ground after discovery. Given Atlas's discovery on the 1st of July 2025 and its high excess speed, people immediately reran feasibility math. Some studies show that the delta V needed from a post-discovery Earth launch would have been enormous and beyond standard launcher propulsion capabilities. Other teams explored alternatives, like launching from other planets or redirecting existing spacecraft that are already far from Earth. For example, a probe based at Mars or a spacecraft already in the outer solar system would need less delta V to reach Atlas than one launched from Earth after discovery. That is simply because the geometry and relative speeds line up better if you start farther out or at a node closer to the comet's path. But getting a craft into the right place ahead of time is the only practical route. People quickly proposed repurposing active spacecraft. For Atlas, there were public discussions about whether Juno, Psyche, JWST, or orbiters around Mars could be turned to observe the object when their orbital timing put them near its path. Those ideas are attractive. A spacecraft already in space has fuel and instruments and may need only modest course changes to record a flyby. The limits are real: fuel, available thrust, mission constraints, and spacecraft health. So whether such redirections are doable depends on each craft. Juno has been suggested because Atlas will pass near Jupiter in 2026. Advocates point to the rare chance to point an existing instrument at an interstellar body. But mission teams must weigh cost, risk, and whether the spacecraft can safely perform the extra maneuvers. If a brand new chase mission were to be attempted, what propulsion choices exist and what would they require? Chemical rockets paired with gravity assists are the simplest, most mature route. They need big launchers and often long, cleverly timed gravity assists, with Jupiter being the main helper. The trade-off is time. Gravity assists often take years and require Jupiter to be in the right place. Project Lyra and other feasibility studies explored multi-assist trajectories that can reduce the onboard delta-V, but at the cost of long flight times and heavyweight launches. For a solar Oumuamua maneuver, one must fly deep toward the Sun, accelerate at perihelion where the spacecraft's speed is highest, and thus get a big bang for the buck from an engine burn. This trick reduces total delta-V, but requires a heat-shielded vehicle and a staged approach to survive the sun dive. It is technically risky, but lowers propellant needs. Several studies indicate solar Oumuamua missions could make otherwise impossible chases somewhat less impossible, at least in principle. High ISP ion engines give more total impulse for less propellant, but low thrust means long spirals to raise orbital energy, which often don't match a fast interceptor's timing needs. Electric propulsion works well for missions with months to years to slowly change velocity or as a booster after gravity assists, but it is not a cure for the huge immediate delta-V gap. Solar sails or laser sails offer continuous acceleration without propellant mass, but require either very large sails or ground space laser arrays. Breakthrough-type concepts could, in time, allow intercept of unexpected fast targets. Today, that technology remains speculative for a rapid, reliable intercept of an object like Atlas. A fast object's V-infinity sets the baseline energetic hurdle. For Atlas, the incoming V-infinity is large, which meant post-discovery delta-V needs were estimated as extremely high, higher than available on most launch options. Some analyses showed it would have been less costly, in delta-V, to launch from Mars, or to use a spacecraft already in the outer system. The longer you wait from discovery, the more energy you need. That is why late chase options collapse quickly. How much payload and what instruments would matter if a mission were possible? Instrument choices follow classic comet/interstellar objectives. A flyby spacecraft would want high-resolution visible images, infrared and ultraviolet spectrometers, a dust analyzer, a mass spectrometer for neutral and ion chemistry, a dust impact detector, a magnetometer and a radio science package to measure bulk mass from trajectory perturbations. If you could go closer, a dust collector or sample return would be the gold standard, but sample return adds huge cost, time and complexity. The ESA Comet Interceptor payload offers a real blueprint for what works: cameras for context, spectrometers to identify volatiles, and dust analyzers to read grain composition. Those instrument types would be the first line on any Atlas Intercept wish list. Comet Interceptor shows the value of being ready, pre-launched, parked and waiting. Project Lyra shows where creative trajectory design and heavy lift can bridge part of the gap, or how solar Oumuamua tricks can reduce propellant needs. Several studies suggested keeping a small, fast-response spacecraft on standby that could be launched quickly to a new target. An idea with political and budgetary hurdles, but also strong scientific logic. The bottom line from those efforts is that catching an arbitrary interstellar visitor on short notice remains vastly tougher than studying one that is slower, or one we can prepare for ahead of time. Finally, there is the pragmatic path many teams now urge: invest in ready missions and in better, faster discovery. The more we find interstellar visitors early, and the more we pre-deploy capable probes at favorable waypoints, such as Sun-Earth L2, Mars staging orbits, outer planet staging, etc., the more likely one of those probes can be turned to a new target. In short, the options are: spend huge energy and money to chase a single fast visitor, repurpose existing spacecraft where feasible, or build and park dedicated interceptors that stand ready. Practically speaking, the third option gives the best balance of risk, cost and science return, and it is the strategy many agencies are now favoring. Planetary defense. Is Atlas a wake-up call for future interstellar threats? Our planetary defense systems are largely built around detecting NEOs. In the United States, NASA's Planetary Defense Coordination Office is tasked with cataloging and tracking such objects. Their strategy is well designed for many comets and asteroids, especially ones that are relatively large, hundreds of meters or more, and whose orbits intersect or approach Earth's orbit. Surveys like Atlas, pan-stars, etc., spot NEOs by scanning the sky repeatedly, finding moving points of light and following them up to compute orbits. These systems are increasingly good at finding NEOs that are big and bright, especially with enough warning time. The 2023 National Planetary Defense Strategy emphasizes improving detection, research, mission planning, emergency preparedness, and international coordination. But interstellar objects like Atlas challenge some of the assumptions of how well these systems work. For one, many of the NEO-focused surveys assume objects bound to the Sun, or at least moving slower relative to the Sun, so detection pipelines often treat extremely hyperbolic or very high excess velocity objects differently, or less efficiently. Secondly, interstellar objects may appear first when they are still far from the Sun and thus faint, moving fast, with little or only CO2 or other volatiles that are harder to detect. That means detection often happens late in the object's journey, giving less warning time. Atlas was discovered when it was 4 to 5 AU from the Sun and already active, but even then, it was difficult to see until it brightened. Lead time is critical. For NEOs, detection of an object approaching Earth with enough time allows opportunities to plan mitigation or deflection, or at least track well to no impact risk. For interstellar objects, because they are coming from outside, they may approach from directions where telescopes can't see easily, toward the Sun or from daylight sky, and with high speed, giving less time to follow, study, and plan. Atlas's case shows some strength. Pre-discovery images from surveys and telescopes allowed astronomers to extend the observational arc, refine the orbit, and understand its brightness and activity earlier. But even then, the warning time, from first detection to perihelion, was only a few months. For an object that might pose risk, that is not long. Because of that, Atlas suggests that for future interstellar threats, improvements are needed. Better sky surveys with broader coverage and more depth. Deeper, more sensitive telescopes that can see fainter objects earlier, especially in regions of sky less observed, such as the southern sky or near solar glare, etc. The Vera Rubin Observatory is expected to increase detection of interstellar objects, perhaps detecting dozens. Some objects are more detectable in infrared, especially those with volatile outgassing or with dust warmed by sunlight, because they emit thermal radiation. Missions like NEO Surveyor are designed to detect NEOs in mid-infrared and could help spot objects that are otherwise faint in visible light. Faster follow-up and more automated alert pipelines are needed. The faster telescopes can get follow-up observations after discovery, the better the orbit. The smaller the uncertainty, the more lead time. Automated analysis and artificial intelligence help reduce human lag. Surveys like Atlas already use deep learning classifiers to speed up detection of real moving objects versus artifacts. Because interstellar objects are rare but potentially hazardous if they arrived on a collision course, policies might need to consider readiness for unknown objects. That could include international cooperation for rapid data sharing, pre-inventoried fast response observation assets, perhaps even pre-positioned spacecraft or missions like the Comet Interceptor, which is designed to wait in a stable orbit, ready to fly by a newly discovered comet or interstellar object. Solar system asteroids and comets are better known in frequency, distribution, and what they do. We have catalogues of many NEOs, especially large ones, and models of impact probabilities. Interstellar objects are much fewer in observed number, and much less is known about typical size, strength, behavior. For example, Atlas's high velocity means if it were on a collision course, impact energy would be vastly greater for the same mass than a slower NEO. Also, unknowns like volatile content, porosity, strength, and shape make it harder to predict exactly what kind of damage or behavior might happen. Interstellar objects may behave differently under heating than solar system comets do. Systems designed for NEOs are good, but interstellar objects push the limits. Speed, motion from unusual directions, faintness early, non-standard composition. They are not typical asteroid crossing Earth's orbit objects. Because of that, we may need to broaden survey strategies, invest in telescopes with better sky coverage, increased infrared capability, better orbit determination tools that account for non-gravitational forces, early and maybe even standby space missions that can be redirected or are waiting for discovery. The planetary defense community is already taking Atlas into account. The discovery was announced via NASA's planetary defense channels. Surveys like Atlas, ZTF and others are contributing pre-discovery data, which helps refine orbit and understand risk. NASA's 2023 Planetary Defense Strategy already lays out improvements in detection, characterization and response. Also, new telescopes such as the Roman Space Telescope and NEO Surveyor are coming online by 2027, which will greatly expand capacity. Roman is expected to improve physical characterization and orbit measurement for many NEOs. Interstellar objects, while rare, present novel risks. A comet that is volatile-rich and comes in fast could fragment or produce dust or interact in ways that make orbital predictions more uncertain. Impact scenarios would be worse than slower NEOs. Atlas is a reminder that while we have many tools, more work remains to ensure that if a less benign interstellar object appeared, we could detect it early and evaluate risk properly rather than in panic. If nothing else, it underscores that the unknown unknowns in interstellar visitors are real, and that planetary defense must account not only for what we know and expect, but also for rare, fast, poorly understood objects. Sample: return from an interstellar object, science, payoff and challenges. The scientific payoff of retrieving material from an interstellar object would be extraordinary because such a sample would be matter literally from outside our solar system. Material formed in another star's disk, cooled in interstellar space, carried by cosmic rays, perhaps very old, perhaps very different in chemistry. From such a sample we could measure isotopic ratios, for example of hydrogen versus deuterium, carbon isotopes, nitrogen, oxygen, etc., which tell us about conditions in the parent system where the object formed. Differences from solar system ratios reveal processes in molecular clouds, in disks around other stars, how planetesimals formed, and how volatile compounds survive or are lost. We could also look for organic molecules, possibly prebiotic compounds, particularly because interstellar objects may preserve some very fragile organics that are hard to preserve in many solar system comets because of solar heating. A sample return mission would allow laboratory measurements such as mass spectrometry, microscopy, and chemical separation that are far more precise and detailed than remote spectroscopy. It would allow analysis of mineral grains, ice composition, tiny inclusions, perhaps trapped gases, trace elements, each giving insight into how the building blocks of planets, comets, and maybe life differ across star systems. According to NASA's Interstellar Object Interceptor Missions report, these objects represent the first known macroscopic samples of exoplanetary material available in our neighborhood for detailed analysis. Furthermore, sample return could reveal the degree of processing the material has undergone, how much radiation damage, thermal alteration, cosmic ray exposure, etc., whether volatiles are primordial or have been altered, whether ice grain phases are amorphous or crystalline, what organics may have been destroyed or preserved. This has implications for understanding how common or rare certain chemical conditions, such as those conducive to prebiotic chemistry, are across the galaxy. There are already studies and mission concept proposals aimed at similar goals. One is titled A Study of an Interstellar Object Explorer, IOE mission. This mentions how a mass spectrometer could constrain coma isotopic ratios, giving information about the parent stellar system. Another concept maps kinds of interstellar object classes to mission types: flyby, rendezvous, sample return. These demonstrate that in engineering and mission design, scientists are already thinking through how to make it happen. The challenges are substantial. The difficulty of catching up to interstellar objects has already been discussed, but another difficulty is the capture of the sample. If the nucleus is active, with strong dust and gas emissions, a spacecraft flying through the coma could be damaged by dust, or sample could be contaminated by gas or dust, not representative of the deeper, more preserved material. Ensuring the sample is from the nucleus, not just loose dust or surface-degraded material, is hard. The sample collector must avoid heating, must preserve volatile compounds, keeping them cold perhaps or freezing them, if possible, to avoid loss of gases or ice. Contamination from the spacecraft or from Earth on return is also a serious concern. You want pristine material. Rendezvous is a huge challenge. Matching speed, catching up or getting close enough to sample requires not only high propulsion, but precise trajectory planning, very good knowledge of the object's path, and stable spacecraft operations. Mission planners have to account for uncertainties in the ISO's orbit, which include non-gravitational forces from outgassing, brightness which affects tracking, possible fragmentation, etc. All of that increases risk. Bringing the sample back safely is another problem. Re-entry to Earth's atmosphere must protect the sample. If the sample contains volatile ices or gases, thermal shielding, cooling, perhaps cryogenic containment may be needed. The travel times could be long, many years to reach the object, then many more to return, depending on orbit and speed. Longer missions increase the risk of failure, of sample degradation, of cost growth. Engineering a mission for sample return from Atlas would also require robust instruments. A sampling mechanism, maybe touch and go or small impactor or scoop, possibly storage at low temperature, dust protection, ability to analyze samples in situ, as well as return to Earth. Also, you need instruments to map the surface, to pick a good sampling site, cameras, spectrometers, mass spectrometers, dust analyzers, and possibly a small subprobe to capture volatile gases. Because Atlas is moving fast and at hyperbolic speed, its trajectory diverges quickly. Opportunity windows when spacecraft launch and intercept are possible are short. For a sample return, you need not just intercept, but also return path, which means more energy, more time, more risk. Coma dust and gas could coat or smear the sample, making it hard to distinguish what part of the sample came from the deep nucleus versus what part was surface dust or gas that has been altered. Flying through the coma, the collected sample could be contaminated by fine dust that has been floating or migrated from processing, or be exposed to UV radiation. That may change the chemical fingerprints one cares about, such as isotopic ratios or volatile content. Despite the challenges, scientists believe the science value is worth thinking deeply about it. The mission concept studies have estimated that, using near-term technology, the sample return mission to an interstellar object is conceivable. They calculate trajectories, delta-V demands, mission durations, and often find that sample return would require either high-energy budgets, large launch vehicles, or waiting missions already in position. For example, the second study showed that flyby, rendezvous, and sample return missions to various classes of interstellar comets or objects are feasible with existing or near-term technology. It is just that the budget risk is large. Sample return would create permanent artifacts. Labs could preserve material for future generations and use newer instruments later. Once the sample is back, many more studies can be done than remote spectroscopy, tiny trace elements, noble gases, trapped gases, microstructures, isotopes that require mass spectrometry with high resolution, etc. Missions that return samples are very expensive and tend to take years or decades from concept to launch to return. Convincing funding agencies and policymakers to invest in preparing for interstellar sample return, which has uncertain payoff, uncertain target appearance, risk of failure, is hard. Some mission proposals, such as Corsair or Caesar for solar system comets, demonstrate how sample return missions work in simpler cases, but extending that to interstellar object sample return has extra unknowns, plus mission risk and mission cost. Still, a sample return from Atlas would not just offer more data, but qualitatively new data. The engineering, cost and risk challenges are formidable, but whether one can reliably do this for Atlas depends on how early it's detected, how well its orbit is known, and whether resources, technology, and mission planning are already prepared in advance. Communication search. Are we listening for technosignatures? Recent literature explicitly discusses interstellar objects as targets for technosignatures, which include signals in radio, optical, infrared, or even unexpected spectral, trajectory, or thermal anomalies. A recent paper, Technosignature Searches of Interstellar Objects, lays out 4 broad classes of technosignature follow-ups: anomalous motion, odd spectral or thermal features, unnatural shapes or reflectivity, and radio or optical transmissions. After the discovery of Oumuamua, scientists did exactly that. They listened in multiple ways. The Allen Telescope Array and the Breakthrough Listen project used the Green Bank telescope to search for narrowband and broadband radio signals from Oumuamua in late 2017. They looked for unnatural transmissions, that is, signals that are not likely to be from natural astrophysical sources, perhaps continuous or pulsed, over several frequency bands. The results: no signals above the detection thresholds were found. Also, serendipitous radio searches were undertaken with the Murchison Widefield Array in Australia. A paper in 2018 searched for narrowband or broadband signals in the 72 to 102 MHz range while Oumuamua was in the field of view. None were found, but the work established upper limits on transmitter power, assuming Oumuamua had been emitting. For Atlas, similar ideas have been proposed or are being discussed. The paper suggests that with interstellar objects or ISOs like Atlas, scientists should use radio telescopes, optical telescopes for laser pulses, or anomalous spectral lines and monitor motion anomalies. It mentions that Atlas and prior ISOs have been observed sufficiently well to test many natural models, and the search for technosignatures is part of the follow-up plan. What kinds of signals would count as technosignatures? Examples include narrowband radio signals that are too clean or stable to come from natural processes, optical pulses that repeat or have spectral properties inconsistent with reflection, thermal excess, aka waste heat, in infrared that does not match what a natural comet would produce, unusual trajectory or acceleration not matched by gas outgassing or radiation pressure, unusual reflectivity or spectral edges that suggest materials unlike typical ices or dust. But there are strong counters and scientific standards that apply. First, absence of detection is not evidence of absence. Just because radio searches have so far found nothing doesn't mean no artificial signals are there. They could be too weak, at frequencies unsearched, intermittent, or be masked by noise. Likewise, natural processes can produce some oddities, such as non-gravitational acceleration, unusual brightness, spectral features, that might at first smell artificial, but upon deeper study are consistent with comet physics. Scientists want to avoid false positives, mistaking a natural phenomenon for something engineered. Standards for claiming anything artificial are high. Usually multiple independent observations, preferably in different domains: optical, radio, infrared, consistency over time, repeatability of signals, ruling out all plausible natural causes, careful calibration of instruments to avoid interference, etc. For example, the radio searches of Oumuamua used multiple telescopes and frequency bands. They set upper limits on signal strength and published null results. The community recognized that the hypothesis of artificial origin for Oumuamua is not ruled out absolutely, but it lacks positive support and must be treated as speculative. There are risks of false alarms. Radio frequency interference from human devices on the ground or satellites can mimic narrowband signals. Optical atmospheric events such as lightning, cosmic rays, or satellite glints can mimic pulses. Spectroscopy may show strange spectral lines if instrument calibration is imperfect. Trajectory anomalies may arise because of dust, non-uniform outgassing, mismodeled forces. So any claim of technosignature has to survive intense scrutiny. In discussion, some researchers argue that interstellar objects like Atlas could play a new role in technosignature searches because they may carry hitchhiked signs of technology, like a dormant probe carried inside a natural body, or artifacts that become exposed when cometary outgassing removes surface material. Some suggest that if there were a probe or technology embedded inside, as the outer layers sublimate, parts of it might become exposed or reveal signs, for example, unusual reflectivity, metallic surfaces, radio emissions if powered. But this remains speculative. In the literature review, authors caution that until more sensitive observations are available, natural models should be treated as the baseline. Another point is about timing. The best times to search are when the object is relatively close, so signals are stronger, when it is active, perhaps exposing buried surfaces, and when observing geometry like the sky position, solar elongation or interference is favorable. For Atlas, because it is active and being observed by many telescopes, conditions are partly good, but challenges remain such as distance, direction, and signal strength. It is possible that in the coming months or years, radio telescopes, optical transient detectors, optical infrared spectrometers will more deeply scrutinize Atlas's emissions for anomalies. But so far, no evidence has been found of artificial signaling or technology. The balance of scientific opinion remains that Atlas is natural, but scientists continue exploring because it is scientifically interesting and because the risk of ignoring strange possibilities is low versus the cost of checking. What Atlas means for our models of planetary system formation. In a recent paper estimating Atlas's age to be between 3 to 11 billion years old, the researchers also estimate that there is about a decent chance that Atlas came from a relatively metal-poor star. That implies that planetesimal formation and ejection are not just processes of rich, massive, metal-heavy systems. They can happen in more metal-poor environments too, since metal content in a star's protoplanetary disk correlates with what solids are available. This suggests that ejection of comet or asteroid bodies may be efficient even in disks that are less rich in heavy elements. A second theoretical idea is that ice lines, the places in protoplanetary disks where certain volatile species freeze out, are more important than sometimes assumed. Atlas's strong CO2 signature suggests it formed beyond the CO2 ice line in its parent disk. That means the disk had cool, volatile ices far out, and that planetesimals formed in those regions, not just close in where water ice is the dominant volatile. That supports models that include multiple ice lines, water, CO2, carbon monoxide, etc. And that bodies forming beyond these lines may be large, volatile, rich, loosely bound, and prone to ejection later. The presence of ice lines influences where bodies accrete, what composition they have, and how easily giant planets or outer planetesimals scatter them out. Another implication touches on ejection rates. How many planetesimals, comets, asteroids are thrown out of systems? An early paper about Oumuamua argued that to explain seeing Oumuamua, planetary systems must eject on the order of about 1 Earth mass of planetesimals per solar mass of stars over the galaxy. If Atlas is more typical than exceptional, then similar ejection rates might be common, meaning there are large numbers of interstellar bodies floating in the Milky Way. The Atlas Age paper notes that finding 3 interstellar objects so far provides stronger statistical constraints, tightening estimates of how many such bodies exist and when they were made. These ideas challenge older models in which planetary system formation was thought to mostly form and retain planetesimals. Traditional models considered that many planetesimals stay in belts, like the Kuiper belt or asteroid belt, or get accreted into planets, growth proceeds, etc. But Atlas suggests that ejection is efficient, possibly more efficient than some models allowed, especially over long timescales. That may mean that many planetary systems lose a large fraction of their small icy or rocky bodies to interstellar space. Some of those models assume that ejected material is dominated by rocky or small fragmented bodies. Atlas's composition suggests also that outer icy material is thrown out, not just rock. If interstellar objects are abundant, then planet-forming disks around young stars might capture some of them. The recent work by Suzanne Faltzner suggests that young disks could gravitationally trap interstellar comets' asteroids, especially around more massive stars, acting as seeds in disks to help overcome barriers in growth of planetesimals, problems where boulders bounce or drift rather than stick. Falseness models show that millions of interstellar objects could be caught per disk, particularly around high-mass stars, which would help speed up planetary growth, especially of gas giants, in systems where disk lifetimes are short. Such seeding challenges previous assumptions that all growth must start locally, from dust grains in that system's disk only. If some of the material is foreign but gets trapped, planet formation may be more messy and more varied than previously thought, with mixing of native and non-native solids. The presence of multiple interstellar objects also places constraints on models of how many such objects exist in the galaxy. Earlier models had wide ranges. Some suggested interstellar planetesimals are very rare, others that they are common. The discovery of Atlas and its speed, size estimates and composition allow better statistical estimates. The paper tries to infer formation rate by comparing the detection of 3 ISOs with survey sensitivities. We can get lower bounds on how many ISOs are out there per volume or per star. That has implications for how many rogue comets there might be drifting in the galaxy, unbound or loosely bound. Some estimates suggest many interstellar comets per star, possibly large numbers such that the galaxy is teeming with them. Because we detect only the brightest, most favorable ones now, many more faint, small or inactive ones likely pass undetected. What this suggests about the variety of exoplanetary systems is that they may differ much more than our solar system does. Systems with giant planets are more able to scatter large planetesimals out. Systems without giants may retain more of their material. Systems around massive stars or in dense star clusters may experience stronger external gravitational perturbations from passing stars or molecular clouds and therefore eject more bodies. Disks that form in metal-poor environments may produce fewer solids or volatile species. Yet Atlas's likely metal-poor origin possibility suggests even those environments can make sizable icy bodies and eject them. The diversity in volatile ratios among ISOs will feed into models of disk chemistry, cooling, stellar irradiation, and migration. Atlas provides empirical constraints on the location of ice lines. Because its volatile composition strongly shows CO2 and its early activity far from the Sun indicates CO2 ice sublimates there, models may adjust where ice lines are placed in disks, how steep volatile gradients are, and how mixing or migration of material in disks works. Furthermore, the age estimates, if Atlas is indeed several billion years old, suggest that ejected bodies can survive for long times in interstellar space without disintegrating completely, meaning that disk formation should produce bodies resilient enough to survive. That may push theories to consider more porous or dust-mantled bodies, protected by outer layers or internal structure that preserves volatiles. There are tensions, though. Some prior models predicted fewer ISOs than what recent detections suggest. Others predicted many, but with smaller sizes or less volatile inventory. If bodies like Atlas are relatively large and volatile-rich, that means that earlier models underestimated either migration, mixing, or retention of volatiles in outer disks, or underestimated the number of ejection events. Also, if ISOs are old, then survival mechanisms over cosmic rays, collisions and thermal cycles must be built into models, which may require larger or better shielded bodies than some models assume. Overall, Atlas forces theory to accommodate ejection not just of small rocky fragments, but sizable icy bodies with preserved volatile chemistry that can survive long journeys. It suggests disks form planetesimals over a wide range of distances, and that many are lost to interstellar space. It suggests a more dynamic, more mixed history of planet formation, with exchanges of material between systems and a galaxy filled with wanderers, many unknown, many yet undiscovered, that carry the diversity of exoplanetary system conditions to us. Where in the Milky Way did Atlas likely originate? One thing known about Atlas is its incoming direction across the sky. Tracing its past path back indicates it comes roughly from the direction of the constellation Sagittarius. Because Sagittarius lies toward the inner galaxy, as seen from Earth, that suggests Atlas came roughly from the inner disk. or at least from a direction that is not purely from the outer disk. But direction alone is not enough to fix birthplace. Along with the motion data, scientists compare Atlas's kinematic properties to those of known stellar populations of the galaxy. These populations differ in their typical velocities, metallicities, ages, and so forth. The idea is, if Atlas's velocity vector and chemical fingerprints align more with thick disk stars, then it likely came from a thick disk environment. If it aligns more with the thin disk, then it came from younger, more metal-rich environments. Finally, if it aligns with the halo, then it came from very old, metal-poor, dwarf galaxies, or accreted systems. Recent research suggests that, while a halo origin cannot be entirely ruled out, the preponderance of evidence favors a thick disk provenance. That means Atlas likely came from a region of the Milky Way whose stars are older, with moderately low metallicity compared with the Sun, with kinematic motion that is more random than typical thin disk stars, and likely outside the plane of the galaxy to some degree. Metallicity is important here. Thick disk stars tend to have iron to hydrogen ratio values moderately below solar and often enhanced alpha element ratios, which include elements like magnesium, silicon, etc., produced in early supernova of massive stars, relative to iron. One paper argues that if Atlas came from the thick disk, then one expects its composition to reflect subsolar metallicity, A enhancement, and possible weaker retention of supervolatiles. Indeed, observations of Atlas show strong CO2 activity. Whether this maps to reduced abundance of other highly volatile species is under study, but theory predicts that in a thick disk environment, subject to more intense radiation early on and perhaps lower metal content, some volatile depletion might be more likely. Thick disk stars are often 8 to 12 billion years old, depending on metallicity among other factors. The thick disk formed during an intense star formation phase between roughly 9.0 and 12.5 billion years ago. If Atlas is associated with the thick disk, then its birth may date from sometime in or after that period. That aligns with other age estimates using its kinematics and speed. The possibility of a halo origin is not entirely excluded. Halo stars or objects are very metal-poor, very old, have highly eccentric orbits around the galaxy, often showing little rotation with the disk and large vertical excursions. If Atlas had halo origins, one might expect even lower metallicity, different chemical abundances, possibly more disrupted volatile content, and possibly a velocity vector more aligned with random motions rather than disk motions. But Atlas's velocity and chemical signature seem more consistent with thick disk than halo models. Sagittarius lies toward the inner galactic disk. If Atlas came from that line of sight, then it may have come from a region nearer the galactic center, though nearer is still thousands of light years away. Inner disk regions tend to have higher densities of stars, potentially more opportunities for planet-forming systems, more gravitational interactions, more radiation exposure. But metallicity in the inner disk can also be higher, so if Atlas came from there, but shows lower metal content, that suggests it either came from inner disk, but a region of lower metallicity, or has been significantly processed. A thin disk origin is less favored. Thin disk stars are younger, often less than 8 billion years old, relatively metal-rich, usually moving on more circular orbits in the plane of the galaxy and with lower velocity dispersion. If Atlas came from the thin disk, then its high velocity would need explanation, either very early ejection or repeated perturbations. But current analysis of Atlas's excess velocity and how random its motion is shows more alignment with thick disk kinematics. Knowing this has implications. It means many of the interstellar objects we detect might be coming preferentially from old systems, thick disk stars, or potentially from birth environments with modest metallicity. That kinds of compositions we see are reflective of those environments. That exoplanetary systems in thick disk had the capacity to form volatile, rich bodies despite lower metals, and that the galaxy may have a large population of old interstellar wanderers from thick disk stars drifting toward us over long times. How often do such large interstellar objects pass through? For decades, astronomers assumed interstellar visitors would be so rare that we might never see one. But in less than a decade, 3 have already been caught. That has forced researchers to re-examine their numbers and ask whether these travelers are actually more common than anyone imagined. The way scientists make these estimates is surprisingly simple in principle, though the details are messy. They look at how long a survey has been running, how much of the sky it covers, how sensitive it is, and how many interstellar objects it has detected. From that, they back-calculate a rough density, how many such objects exist in a given volume of space. For Atlas, the Discovery Survey had been monitoring much of the night sky for about 3 years before it found this interstellar comet. That gives a rough density of about 1 object per 1,000 cubic astronomical units. In plainer terms, if you carved up the local space around us into huge blocks, you might expect to find a large Atlas-like comet in 1 out of every 1,000 of those blocks, but that is only one piece of the puzzle. Astronomers also build computer models to see how many object surveys like Rubin Observatory's Legacy Survey of Space and Time might find once it begins full operations. Those models suggest a wide range. In the most optimistic cases, Rubin could find dozens per year. In more cautious cases, it might only find 1 every year or 2. The difference comes down to assumptions. How big most interstellar objects are, how reflective they are, how fast they move, and whether they show activity like a comet. The lower estimates imagine that most of these bodies are dark, small, and hard to see. In that scenario, we would only notice the rare bright or active ones. The higher estimates assume that there are more moderate-sized objects and that better technology will allow us to notice them even if they are faint. Rubin's deep imaging could be a game changer because it will see far fainter objects than current sky surveys and will cover much more of the sky each night. Atlas is interesting because it extends the size and brightness range upward. Oumuamua was tiny, probably only a few hundred meters across. Borisov was somewhat larger, but still on the small side for comets. Atlas, on the other hand, may be several kilometers wide. Its activity made it easier to spot at a distance. The fact that surveys caught something this large suggests that either big interstellar comets are not as rare as once thought, or that we are only just now reaching the level of sensitivity needed to detect them. There is another way to frame the numbers. If the density of large objects is around 1 per 1,000 cubic AU, then it makes sense that a survey might find one every few years. Smaller ones should be far more common, but they would only be visible when they are very close to Earth, which means most slip past unseen. That also means our current sample is biased toward the larger or brighter bodies. In other words, we are only scratching the surface of what is really out there. Researchers like David Jewett and Darrell Seligman have pointed out that if the higher densities are right, there could be an unimaginable number of these objects drifting through the Milky Way, up to 10 to the power of 25 or more. That number is so large it is almost meaningless on a human scale, but it tells us that planetary systems everywhere are likely ejecting material into space on a massive scale. Our solar system has probably done the same, flinging countless icy rocks into the galaxy over billions of years. Atlas is just one that happened to wander into our field of view. Even so, there are complications that hide many of them. Fast motion makes them harder to catch on images because they streak across the detector. Objects that arrive from the direction of the sun can be missed because no telescope can safely stare into daylight. Faint objects may never be noticed until they are already past. And detection software sometimes filters out unusual motion as an error rather than a real discovery. All of this means the actual rate of interstellar visitors could be higher than our detections suggest. By scaling up, it is possible to imagine how different the future might look with improved instruments. If Rubin Observatory can reach a couple magnitudes fainter in brightness, that expands the volume of space in which it can detect interstellar comets. The larger the volume, the more likely we are to spot them, and the more accurate our statistics will become. Instead of seeing one every few years, astronomers might find several per year. That would turn interstellar objects from rare curiosities into a steady part of observational astronomy. Not long ago, the idea of finding even one interstellar comet was treated as a once-in-a-lifetime event. Now scientists are preparing for a steady flow of them, some small and strange like Oumuamua, some more classical like Borisov, and others large and active like Atlas. Each new discovery is helping to refine the numbers, close the gaps, and show us how common these wandering bodies really are. Limits to our knowledge. What we still don't know about Atlas. Much of what we know about Atlas is surrounded by wide uncertainty. One of the biggest gaps is its actual size. We have an upper and lower limit from Hubble, but the size range is fairly large, and where it ends up in that range changes quite a bit else about it. Its shape and how it spins are also a mystery. Some faint variations have been reported, but the evidence is weak, and no one can say with confidence if the nucleus is rotating in a steady way or tumbling chaotically. We also do not know if it is dense and compact or light and porous. Is there a crust that shields hidden ices, or does gas escape freely through cracks? These questions matter because the internal structure decides how Atlas responds to heating, how quickly gases escape, and how likely it is to break apart. Observations so far suggest that volatile gases such as carbon dioxide and carbon monoxide are abundant and not buried too deeply. But we do not yet know the full picture. The mix of gases is only partly known. We still lack detail about the full chemical inventory. Trace gases, organics and noble gases are difficult to measure, and even for water, some of the signal may be coming from icy grains in the coma rather than the nucleus itself. This uncertainty makes it hard to judge exactly what the body is made of, or what processes shaped it in its home system. Another open question is whether its outgassing produces measurable changes in its motion. When a comet vents gas, the escaping material can act like tiny thrusters, giving the body a slight push. For Atlas, models suggest that the gas and dust escaping could add up to noticeable non-gravitational forces. But whether these are strong enough to shift its orbit in a detectable way depends on its size and mass, which again are uncertain. A small, light nucleus would be more easily pushed around than a larger, heavier one. Many comets have been seen to split apart when they get closer to the Sun. Some disintegrate completely. Atlas has already shown strong dust activity, which could be an early sign of surface erosion, but so far, no large pieces have been seen breaking off. Whether it will survive its journey intact or leave behind fragments is still an open matter. Scientists often assume a dark surface similar to known comets, but if Atlas is darker or brighter than this assumption, the size and mass estimates change dramatically. Because the dust coma adds so much extra brightness, separating out the nucleus's true reflectivity has so far been impossible. The age range that we have for Atlas is also quite large. The numbers are rough, and they leave a wide range of possibilities. Even its trajectory into the solar system is not fully nailed down. Many images before and after discovery help constrain its orbit, but small errors still remain. These small differences matter because they affect where scientists think it came from, what stars it may have passed near, and what its speed was before entering our system. We don't know the exact size distribution of grains, their composition, or how reflective they are. These grains influence how the coma looks, how heat is carried away from the nucleus, and how gases escape. Without better measurements, models of activity remain rough guesses. Mass is especially difficult to pin down. Without knowing size, density, and structure, the best anyone can do is estimate. Depending on which assumptions you make, the total mass can vary by orders of magnitude. Some suggest it could be much heavier than first thought, while others believe it is light and fragile. The truth is likely somewhere in between, but with such uncertainty, firm conclusions are impossible. The coming months and years will help answer some of these questions. As Atlas nears and passes its closest approach to the Sun, telescopes will track whether its brightness changes suddenly, whether any fragments appear and whether its path shifts slightly due to outgassing. More detailed spectroscopy will help reveal minor gases, while longer stretches of photometric monitoring might finally give clues about its rotation. But for now, many of the key details remain unsettled. Preparing for the unexpected. Infrastructure for future interstellar hunters. Surveys like ATLAS already do wide sky coverage repeatedly, catching moving objects each night. Expanding such networks, adding telescopes in different continents with different filters, better sensitivity, would help catch faint or fast interstellar objects earlier. It has been estimated that Rubin's 10-year survey might detect somewhere between 6 and 51 interstellar objects in that time span, depending on how bright and how large typical ISO nuclei are. Once a candidate is spotted, astronomers need to point as many telescopes as possible toward it. This means mobilizing optical, infrared, ultraviolet, and even radio instruments quickly before the object moves into a position where the sun's glare, the Earth's rotation or bad weather blocks the view. Robotic telescopes or systems that can be rapidly redirected are essential for this stage. Coordinated observing campaigns, pre-approved observing time and fast data sharing allow researchers to maximize the window of opportunity while the object is still visible. To make this possible, astronomers rely on real-time alert systems. Modern surveys generate staggering amounts of data every night, and hidden within that flood are the rare signals of interstellar objects. The Rubin Observatory will produce millions of alerts per night. Alert brokers, systems like ALERS, Antares, Babamul, Fink, and Lasser, are designed to sift through these alerts, classify them, and flag the ones that deserve immediate attention. Other platforms, such as TransientVerse, work to integrate alerts from multiple sources, highlight unusual behavior, and assist in planning follow-up observations. Without these automated systems, most unusual objects would be lost in the noise. Amateur astronomers also play a key role. Once an object is discovered, smaller telescopes can continue to monitor it, collecting light curves, measuring changes in brightness, and even checking older images for pre-discovery traces. The Minor Planet Center already accepts high-quality data from amateurs, but building stronger connections between amateur and professional efforts would improve global coverage. Training, standardized reporting methods, and calibration systems could make the contributions of amateurs even more valuable, especially when dealing with rare and fast-moving targets. Archival image mining has proven to be a powerful tool. Making survey archives easier to search, with clear metadata about sky coverage and detection limits, would greatly improve the accuracy of orbit calculations and physical models. Wide-field telescopes that can cover large areas of sky quickly are essential for discovery, but follow-up studies require more specialized tools. Sensitive infrared telescopes can detect volatile gases sublimating at great distances, while ultraviolet instruments can reveal chemical signatures invisible from the ground. High-resolution imaging can separate the nucleus from the surrounding coma and tail. Distributing telescopes across multiple longitudes on Earth also ensures that observations are not interrupted by the day-night cycle. No single observatory or nation can cover the entire sky or every wavelength of light. International coordination, open standards for data formats and systems like VO Event for distributing alerts make it possible for scientists worldwide to contribute pieces of the puzzle. Prioritization tools also matter. Not every moving dot in the sky is an interstellar object, and researchers must decide which candidates are worth immediate follow-up. Tools like AAS2RTO are being built to help identify the most promising alerts. The sheer volume of data requires automated pipelines capable of handling millions of detections per night. The Zwicky Transient Facility, for instance, distributes over 1 million alerts nightly, often within seconds of detection. Being able to filter out false signals, identify real moving objects, and trigger rapid responses is central to readiness. Finally, all of this depends on policies and funding. Building and maintaining survey telescopes, alert brokers, and follow-up networks requires long-term investment. Funding is also needed for archival data access, public data releases, and rapid response observing campaigns. Even more ambitious is the idea of reserving resources for fast spacecraft missions that could be launched on short notice. Taken together, these elements form the foundation of a new kind of infrastructure, with wider surveys, smarter alert systems, stronger follow-up networks, archival mining, dedicated spacecraft, global collaboration, and steady support. Humanity could move from the rare, lucky discoveries of the past toward a future where interstellar objects are caught, tracked, and studied as a matter of routine. When the next strange visitor like Atlas appears, the scientific community would be ready, not scrambling but prepared to measure, analyze, and perhaps even reach out to touch a piece of another star system. How many other interstellar objects do you think we'll find in the upcoming years? Will they be more of the same, or will the new ones continue surprising us by how different they are from the ones that came before? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.